Welcome to the calmest corner of the coding world. Find a comfortable spot, dim the lights, and let your body sink into relaxation. This tutorial is designed to flow like a gentle breeze, guiding you through Dart with ease and peace. Breathe in, breathe out, and let the rhythm of learning wash over you. If you're feeling the calm, hit that like button and subscribe for more soothing coding sessions. Let's begin. Welcome to the introduction to Dart programming. Today, we will explore the fundamentals of Dart, including its syntax, environment setup, and core concepts. By the end of this session, you will have a clear understanding of what Dart is, how to set up your development environment, and the essential building blocks of the language. We will also cover key topics such as Dart features, installation steps, writing your first program, and foundational programming concepts. Let's begin by understanding what Dart is and why it is a powerful choice for modern application development. Dart is a client-optimized programming language designed to create fast and responsive applications across multiple platforms. Developed by Google, Dart is open source, which means it is freely available for anyone to use and contribute to. Its cross-platform capabilities allow developers to write code once and deploy it on mobile, web, and server-side environments. For example, Dart is widely used in the Flutter framework for building high-performance mobile applications. Whether you are targeting iOS, Android, the web, or even desktop platforms, Dart provides a consistent and efficient development experience. This versatility makes Dart an excellent choice for developers aiming to build applications that work seamlessly across different devices and operating systems. Dart offers several key features that make it a modern and powerful programming language. First, it is strongly typed, which means variables have specific data types, but it also allows optional type annotations for flexibility. This helps catch errors early during development. Dart also supports asynchronous programming through the use of async and await keywords, making it easier to handle tasks like network requests or file operations without blocking the main thread. Another standout feature is Hot Reload, which allows developers to see changes in their applications instantly without restarting the app, significantly speeding up the development process. Finally, Dart includes null safety, a feature that helps prevent null reference errors by ensuring variables are explicitly marked as nullable or non-nullable. These features collectively enhance productivity, reliability, and developer experience. To begin working with Dart, you need to set up your development environment. The first step is to install the Dart Software Development Kit from the official website. Once installed, you can choose an integrated development environment to write your code. Popular options include Android Studio, Visual Studio Code, and IntelliJ, each offering tools and plugins tailored for Dart development. After installing the SDK and selecting your preferred IDE, it is important to verify the installation. You can do this by opening a terminal or command prompt and typing the command Dart version. If the installation is successful, this will display the version of Dart installed on your system. A properly configured environment ensures you can start writing and testing Dart code efficiently. Understanding Dart syntax is essential for writing effective code. Variables in Dart can be declared with explicit types, such as int x equals 5 or string name Dart, or you can use the var keyword for implicit typing. Functions are defined using the void main syntax, as seen in the main function that serves as the entry point of a Dart program. Control structures like if, for, while, and switch allow you to manage the flow of your program based on conditions and loops. For example, an if statement checks a condition and executes a block of code if the condition is true. Dart also enforces null safety, which requires you to explicitly mark variables as nullable using the question mark symbol, such as string, name, to avoid unexpected null values. These syntax elements form the foundation of Dart programming and enable you to build structured and reliable applications. Let's look at an example of a simple Dart program. The code starts with the void main function, which is the starting point of any Dart application. Inside the function, the print statement outputs the text, "Welcome to Dart," to the console. This basic program demonstrates the structure of a Dart file and how to use the print function to display information. To run this program, you would save the code in a file with a Dart extension, such as Hello Dart, and then execute it using the Dart run command followed by the file name. This process allows you to test and see the output of your code immediately, making it easy to experiment and learn. As you progress, you will build more complex programs using the concepts introduced here. In summary, Dart is a versatile, efficient, and beginner-friendly programming language that offers a wide range of features to to support modern application development. Its setup process is straightforward, with clear documentation and tools to help you get started quickly. By mastering the basics covered in this session, you will be well equipped to explore more advanced topics in Dart. In our next session, we will dive deeper into Dart data types and operators, expanding on the foundational knowledge you have gained today. Thank you for your attention, and I look forward to continuing this journey with you. Today, we will explore how to set up your development environment for working with the Dart programming language. A solid setup is essential because it ensures a smooth workflow, reduces errors, and helps you focus on writing code rather than troubleshooting. We will cover the key components you need to configure, including your integrated development environment, the Dart Software Development Kit, project structure, and additional tools. By the end of this session, you will have installed all necessary tools, configured your environment, and verified that everything is working correctly. Let's begin by discussing how to choose the right tools for your needs. When selecting an IDE or editor for Dart development, there are several options to consider. Visual Studio Code, often referred to as VS Code, is a popular choice due to its lightweight nature and strong support for Dart through dedicated plugins. It offers features like intelligent code completion, debugging, and a user-friendly interface. For those who plan to work with Flutter, Android Studio, or IntelliJ IDEA are excellent alternatives. These tools provide deeper integration with Flutter's features and are ideal for building cross-platform mobile applications. However, if you are focusing solely on Dart, VS Code is a more efficient and straightforward option. Choose the one that best fits your project requirements and personal preferences. Next, we will install the Dart Software Development Kit, or SDK. The Dart SDK is the core toolset that enables you to compile, run, and manage Dart code. To get started, visit the official Dart website at dart.dev and download the version of the SDK that matches your operating system, whether it's Windows, Mac OS, or Linux. Once downloaded, follow the installation instructions provided. After installation, it is crucial to add the Dart executable to your system's path variable. This step allows you to access Dart commands directly from the terminal or command prompt, making it easier to manage projects and dependencies. Let's walk through the steps to ensure this is done correctly. Now that that the SDK is installed, we need to set up a dedicated project directory. Creating a specific folder for your Dart projects helps keep your work organized. To initialize a new project, use the command Dart create, followed by the name of your project. This command generates a standard project structure with key folders and files. The lib folder is where you will write your Dart code. The bin folder is for executable scripts, and the pubspec.yaml file manages dependencies. Understanding this structure will help you navigate and expand your projects more effectively as you progress. In this step, we will install the required tools that complement the Dart SDK. The Dart command line interface includes tools like Dart, which runs your code, pub, which manages packages, and Dartfont, which formats your code for consistency. If you are building cross-platform applications, you may also need to install the Flutter SDK. To verify your installation, open a terminal and type Dart-version to check the Dart version. Similarly, use Flutter-version to confirm Flutter's presence. These checks ensure that your tools are correctly installed and ready for use. Configuring environment variables is a critical step to ensure your system recognizes the Dart and Flutter executables. On Windows, you will need to add the path to the pubcache bin directory, which is typically located in your user folder. For Mac OS and Linux, the path might look like /flutter/bin or /pubcache/bin. These paths allow your terminal to locate and execute Dart and Flutter commands without specifying the full file path. If you encounter issues later, double-check that these paths are correctly added to your system's environment variables. Now, let's verify that everything is set up properly. Start by running Dart-version to confirm the Dart SDK is installed. If you installed Flutter, run Flutter-version as well. Next, create a simple Dart file named hello.dart and write a basic print statement. Execute the file using the Dart command followed by the file name. If everything works, you should see the output in your terminal. This test ensures that your environment is ready for development. Even with careful setup, issues can arise. If you encounter problems, first check that the path variable is set correctly. Sometimes, reinstalling the SDK or updating environment variables resolves these issues. Another common problem is using an outdated version of the SDK. Make sure to update to the latest stable release. if multiple versions of Dart or Flutter are installed, they may conflict. Use tools like Flutter version or Dart version to check which version is active and ensure only one is in use. Troubleshooting these issues will help maintain a stable development environment. To recap, we have covered selecting an IDE, installing the Dart SDK, setting up a project directory, and verifying your tools. Now, take a moment to practice by creating a simple Dart file and running it. This hands-on experience will reinforce what you've learned. In our next session, we will dive into writing your first Dart program and explore the language's syntax basics. With a solid foundation in place, you are now ready to begin building applications with Dart. Let's move forward and explore the possibilities. Dart syntax is designed to be intuitive and easy to learn, drawing inspiration from C-style languages such as Java and JavaScript. This similarity makes it accessible for developers familiar with those languages. The core focus of this section is on understanding the structure of Dart code, including how to declare variables, manage control flow, and define functions. Readability and simplicity are central to Dart's design philosophy, ensuring that code is both efficient and easy to maintain. One of the most significant features of modern Dart is null safety, which helps prevent null reference errors by enforcing strict rules about when and how variables can hold null values. This feature is essential for building robust and reliable applications. When working with variables in Dart, you have multiple options for declaration. The keyword var allows the compiler to infer the type of the variable based on the assigned value. The dynamic keyword is used when the type is not known at compile time, but this should be used sparingly. For explicit type declarations, you can use types such as int, string, or double. For example, int age equals 25, or string name, Dart. Dart also provides final and const for handling immutable values. Final is used for values that are assigned once, but can be determined at runtime, while const is for values that are known at compile time. Null safety is integrated into the language through the use of question marks and exclamation marks. A question mark indicates that a variable can hold a null value, while an exclamation mark is used to assert that a variable is not null when accessing its properties. Control structures in Dart allow you to manage the flow of your program. The if else statement is used to execute different blocks of code based on conditions. Loops such as for, while, and and do while enable repetitive tasks, with each loop type suited to specific scenarios. For example, a for loop is ideal when you know the number of iterations in advance, while a while loop continues as long as a condition is true. The switch statement is useful for handling multiple conditions in a clean and organized way. Dart also includes null-aware operators to handle cases where variables might be null. The double question mark operator provides a default value if the left-hand side is null, and the question mark dot operator allows safe access to properties or methods of an object that might be null. Functions in Dart are defined with a return type, function name, and parameters. For example, void greetString name equals print hello name demonstrates a simple function that takes a string parameter and prints a message. Dart supports optional parameters, which can be either positional or named, allowing for greater flexibility in function calls. Named parameters are specified with curly braces, making the code more readable. Functions can also be written using arrow syntax for single expression functions, which simplifies the code. This approach is particularly useful for short, concise functions. Understanding how to structure and use functions effectively is crucial for writing modular and maintainable Dart code. Comments and code structure play a vital role in making your Dart code clear and maintainable. Single-line comments start with 2 forward slashes, while multi-line comments are enclosed in slash asterisk and asterisk slash. Documentation comments marked with 3 forward slashes are used to generate API documentation for your code. Proper indentation and spacing help readers understand the structure of your code, making it easier to navigate and debug. Organizing code into logical sections, such as separating functions and classes into distinct blocks, enhances readability. These practices are especially important when working on larger projects or collaborating with other developers. Mastering the basic syntax of Dart is the foundation for building efficient and scalable applications. Pay close attention to variables, control flow, and functions, as these elements form the backbone of any Dart program. Practicing null safety and maintaining clean code structure will help you avoid common errors and improve the reliability of your code. As we move forward, the next session will delve into advanced data types and object-oriented concepts, which which will expand your ability to design complex applications. By building a strong understanding of these fundamentals, you will be well equipped to explore more advanced topics in Dart development. Variables serve as temporary storage locations in a computer's memory, allowing programs to hold and manipulate data during execution. Data types are essential because they define the nature of the data a variable can contain, ensuring that operations performed on the data are valid and efficient. Understanding variables and data types is crucial for any programmer, as they form the foundation of how data is handled in code. Dart, a versatile programming language, supports both primitive data types like integers and strings, as well as non-primitive types such as lists and maps, offering flexibility for various programming tasks. In Dart, variables can be declared using the keyword var, which allows the compiler to infer the type based on the assigned value. This is useful for quick prototyping, but may reduce clarity in complex scenarios. The dynamic keyword is used when a variable's type might change over time, though this can lead to runtime errors if not managed carefully. For explicit control, developers can specify the type directly, such as int for whole numbers, string for text, or double for decimal values. For example, var name Dart relies on type inference, while string name Dart explicitly defines the variable's type, ensuring consistency and reducing ambiguity. Dart's primitive data types include int, which represents whole numbers like 42, and double, which handles floating point numbers such as 3.14. Strings are used for textual data like hello and booleans or bool, store logical values of true or false. The num type acts as a superclass for both int and double, allowing variables to hold either type. These primitive types are fundamental for basic data manipulation, enabling developers to perform arithmetic operations, comparisons, and string concatenation efficiently. Their simplicity makes them ideal for scenarios where direct data handling is required without additional complexity. Non-primitive data types in Dart, such as list, map, and set, provide more structured ways to organize and manage data. A list is an ordered collection of elements, allowing duplicates and indexed access, making it suitable for sequences of items. Maps store key value pairs, such as name, Dart, enabling efficient lookups by unique keys. Sets contain unique elements, ensuring no duplicates, which is useful for membership checks. The object class serves as the base for all Dart objects, providing common methods and properties that can be inherited by other types. These non-primitive types are essential for building complex data structures and managing relationships between data elements. Dart's type inference feature allows the compiler to automatically determine the type of a variable based on its initial value, simplifying code writing. For instance, var age equals 25 would be inferred as an int type. This reduces boilerplate code, but can sometimes lead to confusion if the type is not immediately clear. To maintain clarity, developers should avoid using var when the type is ambiguous or when the variable's purpose is not obvious. Instead, using final or const for variables that should not change can enhance code safety and readability, ensuring that values remain consistent throughout the program's execution. Final variables in Dart are assigned a value once and remain constant after that, making them ideal for values that should not change during runtime. Constants declared with const are evaluated at compile time and are immutable, offering performance benefits. For example, final pi equals 3.14 sets a value that cannot be modified after initialization, while const pi equals 3.14 ensures the value is fixed at compile time. The const keyword requires expressions that can be resolved at compile time, making it stricter but more efficient for scenarios where values are known in advance. Choosing between final and const depends on whether the value needs to be determined at runtime or can be fixed during compilation. Adhering to best practices when working with variables enhances code quality and maintainability. Using descriptive names, such as username instead of you, improves readability and makes the code easier to understand for others. Preferring final over var helps prevent unintended modifications, reducing potential bugs. Avoiding unnecessary typecasting ensures that operations are performed on the correct data types, preventing runtime errors. Limiting the scope of variables to the smallest possible context minimizes side effects and improves code efficiency. These practices contribute to writing clean, reliable, and scalable Dart applications. Variables and data types are the cornerstone of Dart programming. enabling developers to structure and manage data effectively. Understanding the distinction between primitive and non-primitive types allows for more efficient code, as each type is suited to specific tasks. Leveraging type inference and constants helps create concise and robust code, while adhering to best practices ensures clarity and maintainability. By applying these concepts in real-world scenarios, such as building user interfaces or processing data, programmers can develop efficient and reliable Dart applications that meet the demands of modern software development. Operators are symbols that perform operations on variables and values. They allow you to manipulate data, such as adding numbers, comparing values, or combining conditions. Expressions are combinations of variables, constants, and operators that evaluate to a single value. For example, a simple expression might be a number plus another number, while a more complex one could involve multiple operations and variables. Understanding operators and expressions is essential for writing dynamic Dart code, because they form the foundation of logic and calculations in any program. Without them, you wouldn't be able to create interactive or responsive applications. Dart includes several types of operators, each serving a specific purpose. Arithmetic operators handle mathematical operations like addition, subtraction, multiplication, and division. Relational operators compare values and return a Boolean result, such as whether one number is greater than another. Logical operators combine Boolean expressions, allowing you to create complex conditions. Assignment operators simplify the process of assigning values to variables, while null-aware operators help manage null values safely. These operators work together to provide flexibility and efficiency in Dart programming. Arithmetic operators perform basic mathematical operations. For instance, the plus operator adds two numbers. The minus operator subtracts one from another, and the multiply operator calculates the product. The divide operator returns the quotient, and the modulus operator gives the remainder after division. Increment and decrement operators are used to increase or decrease a value by one, with the placement of the operator determining whether the operation occurs before or after the value is used. These operators are fundamental for calculations in any program, from simple math to complex algorithms. algorithms. Relational operators compare values and return a Boolean result, either true or false. For example, the equality operator checks if two values are the same, while the inequality operator verifies if they are different. The greater than and less than operators can compare numerical values or string values based on their lexicographical order. These operators are essential for making decisions in code, such as determining if a user's input meets certain criteria, or if a condition is met for a loop to continue. Logical operators combine Boolean expressions to create more complex conditions. The AND operator returns true only if both expressions are true, making it useful for requiring multiple criteria to be satisfied. The OR operator returns true if at least one of the expressions is true, allowing for flexible conditions. The NOT operator inverts the result of a Boolean expression, which is helpful for checking the opposite of a condition. These operators are critical for building decision-making structures in Dart programs. Assignment operators simplify the process of assigning values to variables. For example, the += operator adds a value to an existing variable and assigns the result back to it. The null-aware assignment operator only assigns a value if the variable is currently null, preventing unexpected behavior. The null-aware operator provides a default value if the left operand is null, ensuring that your code handles missing data gracefully. These operators make your code more concise and readable while reducing the risk of errors. Expressions in Dart can be as simple as a single number or as complex as a combination of variables, operators, and functions. For instance, a simple expression might be a number multiplied by another, while a complex one could involve nested operations and conditional checks. Expressions are evaluated based on operator precedence, which determines the order in which operations are performed, and associativity, which defines how operators of the same precedence are grouped. Understanding these rules is crucial for writing correct and predictable code. Operator precedence determines the order in which operations are evaluated in an expression. For example, multiplication typically occurs before addition, unless parentheses are used to change the order. Parentheses can override default precedence, allowing you to control the sequence of operations explicitly. Associativity defines how operators of the same precedence are grouped, such as left to right for addition and subtraction, or right to left for assignment operators. These concepts ensure that expressions are evaluated consistently and as intended. Common expressions in Dart include calculations that involve multiple steps, such as multiplying a number by the sum of two others. For instance, a total might be calculated by multiplying a quantity by a price. Logical expressions often combine conditions, like checking if a user's age is above a certain threshold and their status is active. Null-aware expressions handle cases where a value might be missing, such as using a default value if a variable is null. These examples illustrate how operators and expressions are used to solve real-world programming problems. Operators and expressions are fundamental to Dart programming, enabling you to perform calculations, make decisions, and manage data efficiently. Mastering their usage allows you to create complex logic and build robust applications. Practicing with operators in diverse scenarios helps reinforce your understanding and improves your ability to write clean, efficient code. By becoming proficient with these concepts, you'll be better equipped to tackle challenging programming tasks and develop high-quality Dart applications. Control flow statements are fundamental to programming because they determine the order in which code executes. Imagine a program as a road trip where the driver follows a specific route. Without control flow, the code would run in a straight line. But with these statements, we can create decisions, repetitions, and branching paths. Conditional logic allows us to check if a certain condition is true or false. Loops let us repeat tasks efficiently, and branching mechanisms like switches help us handle multiple possible scenarios. These tools are essential for building dynamic applications in Dart, where user interactions, data processing, and real-time responses require precise control over execution flow. Conditional statements are the building blocks of decision-making in code. The if statement checks a condition, and if it is true, it executes the corresponding block of code. The else clause provides an alternative path when the condition is false. When there are multiple conditions to evaluate, else if allows us to chain additional checks. For example, if a variable x is greater than 5, we perform one action, but if it is not, we check another condition. The switch statement is particularly useful when comparing a single value against multiple possible cases such as checking the value of a variable and executing different code blocks for each match. This structure makes the code more readable and efficient when dealing with discrete options. Switch case statements provide a structured way to handle multiple possibilities based on the value of an expression. When you use a switch, the program evaluates the expression and matches it against each case label. If a match is found, the corresponding code block runs. If no match is found, the default case acts as a fallback. Dart supports switch with enums, strings, and integers, making it versatile for different scenarios. For instance, if you have a variable representing a color, you can use a switch to handle each color separately, ensuring that the code responds appropriately to each possible input. This approach is cleaner than using multiple nested if-else statements, especially when there are many possible values to check. Loops are essential for repeating tasks without writing redundant code. The for loop is ideal when you know exactly how many times you want to repeat a block of code, such as iterating over a list of items. The while loop continues executing as long as a specified condition remains true, making it suitable for situations where the number of iterations is unknown. The do-while loop is unique because it guarantees that the code inside the loop runs at least once before checking the condition. This is useful when you need to perform an action first and then decide whether to continue. For example, a do-while loop could be used to prompt a user for input and then validate it. Each loop type has its own use cases, and choosing the right one can improve both efficiency and readability. The break and continue statements are powerful tools for managing loop execution. The break statement immediately exits a loop or a switch block, allowing you to terminate the process when a specific condition is met. For instance, if you are searching for a value in a list and find it, you can use break to stop further iterations. The continue statement, on the other hand, skips the current iteration of a loop and moves to the next one. This is useful when you want to bypass certain elements in a sequence without stopping the entire loop. Together, these statements give you fine-grained control over how your code runs, helping you avoid unnecessary computations and improve performance. Null-aware operators in Dart are designed to handle situations where a value might be null, which is a common concern in modern programming. The operator, also known as the null coalescing operator, returns a default value if the left operand is null. For example, if a variable might be null, you can use result equals default to assign a fallback value. The operator allows you to safely access properties or methods of an object that might be null, preventing runtime errors. The operator, or null-aware cascade, applies a series of operations to an object only if it is not null, making it a concise way to handle optional chaining. These operators are crucial for writing robust code that gracefully handles missing or undefined values. Best practices for control flow ensure that your code remains clear, maintainable, and efficient. Keeping conditions simple and readable is vital, as complex logic can lead to bugs and make the code harder to understand. Avoiding deeply nested loops or conditionals helps prevent the arrowhead pattern, where code becomes difficult to follow. Using switch statements for multiple discrete cases is more efficient and readable than lengthy if-else chains. Additionally, always handle edge cases, such as null values or unexpected inputs, to make your applications more resilient. By following these guidelines, you can create Dart code that is not only functional, but also easy to debug and extend over time. Control flow statements are the backbone of program logic, enabling developers to create dynamic and responsive applications. Mastering if-else conditions, switch cases, and loops allows you to structure your code effectively, while flow control mechanisms like break and continue provide precise management over execution. Applying best practices ensures that your Dart code is clean, efficient, and maintainable. As you continue to develop your skills, remember that understanding control flow is key to solving complex problems and building high-quality software. By leveraging these concepts, you can write code that is both powerful and easy to work with. Functions are essential building blocks in programming that allow us to encapsulate logic into reusable code segments. By defining a function, we can execute a specific task multiple times without rewriting the same code, which makes our programs more efficient and easier to maintain. This modularity helps in organizing code into logical sections, making it simpler to debug and update. In Dart, functions come in two main forms: named functions, which have a specific identifier, and anonymous functions, which are often used as callbacks or in higher order functions. Understanding both types is crucial for writing flexible and powerful Dart applications. The structure of a function in Dart follows a clear syntax. It begins with the return type, which specifies the data type of the value the function will produce. Next is the function name, which should be descriptive of the task it performs. Parameters are then listed inside parentheses, and the function body is enclosed in curly braces. For example, the function int addend a int b return a plus b defines a function that takes two integers and returns their sum. Functions can exist independently in the code or be part of a class where they are known as methods. This flexibility allows developers to structure their code in a way that best suits the problem they are solving. Parameters are the variables that a function uses to receive data from the caller, while arguments are the actual values provided when the function is invoked. For instance, if a function is defined with parameters a and b, the arguments passed could be 3 and 5. Parameters can be required, meaning they must be provided when the function is called, or optional, allowing the function to operate with default values. This distinction is important because it determines how the function is used and how robust it is in different scenarios. By carefully designing parameters, developers can create functions that are both versatile and easy to use. In Dart, the type system is designed to infer the data type of variables and parameters automatically, which reduces the need for explicit type declarations. However, specifying types explicitly is often recommended for clarity, especially in complex code bases. For example, a function like void print message string message clearly communicates that it expects a string argument. Parameters can accept any data type, including primitive types like integers and strings, as well as custom classes defined by the developer. This versatility makes functions adaptable to a wide range of tasks, from simple calculations to complex data manipulations. Default values in function parameters provide a way to make certain arguments optional, which enhances the usability of functions. For example, a function like void greet string name, string greeting equals hello, allows the caller to omit the greeting parameter, using hello as a fallback. This feature is particularly useful when a function has many parameters, as it reduces the need for multiple overloads and simplifies the function signature. By setting sensible defaults, developers can create functions that are both flexible and intuitive, enabling users to focus on the essential inputs without being overwhelmed by optional ones. Named parameters allow developers to specify arguments by their names rather than their positions when calling a function. This is especially helpful for functions with many parameters, as it makes the code more readable. For instance, a function like calculate area double width, double height can be called with named parameters such as calculate area width 10, height 5. This approach eliminates confusion about which value corresponds to which parameter, making the code easier to understand and maintain. Named parameters also enable developers to skip certain parameters if they are optional, further increasing the function's flexibility. Optional parameters, denoted by square brackets, provide another way to make function arguments non-mandatory. For example, a function like void log message string message can be called with or without the message argument. This is useful when the function can operate with a default value, or when the presence of the argument is not critical. Optional parameters are particularly valuable in scenarios where the function needs to handle varying input scenarios, such as logging messages that may or may not be provided. By using optional parameters, developers can create more adaptable and user-friendly functions. In Dart, functions can be treated as first-class citizens, meaning they can be passed as arguments to other functions. This concept is central to higher-order functions, which are functions that take other functions as parameters or return them as results. For example, a function like void execute function callback equals callback demonstrates how a function can accept another function as an argument and execute it. This capability is widely used in callbacks, event handlers, and asynchronous programming, enabling developers to create modular and reusable code. By leveraging functions as parameters, developers can design more dynamic and responsive applications. Closures are a powerful feature in Dart that allows functions to capture and retain access to their surrounding environment. This means a closure can access variables from the scope in which it was defined, even after that scope has finished executing. For instance, the function multiply by int x equals int y equals x multiplied by y creates a closure that retains the value of x when it is called later. Closures are particularly useful in scenarios like asynchronous operations, where a function may need to access variables from an outer context. They also play a key role in functional programming paradigms, enabling developers to create more expressive and concise code. Mastering functions and parameters is fundamental to writing effective Dart code. These concepts form the backbone of any application, allowing developers to structure their code in a way that is both efficient and maintainable. By leveraging named, optional, and default parameters, developers can create functions that are adaptable and user-friendly. Practicing these techniques helps build a deeper understanding of Dart's capabilities and improves overall coding efficiency. As you continue to explore Dart, remember that well-designed functions and parameters are key to writing clean, scalable, and robust applications. Lists and maps are fundamental tools in the Dart programming language that allow developers to organize and manage data efficiently. A list is a collection of elements stored in a specific order, making it ideal for scenarios where the sequence of items matters. For example, a list could represent a sequence of tasks to complete or a series of numbers in a mathematical problem. On the other hand, maps are used to store key value pairs, which provide a way to look up data using a unique identifier. This is particularly useful when dealing with structured data, such as user information, where each user has a unique ID. Both data structures are essential in app development because they help manage complex data relationships and improve the performance of applications by enabling quick access and manipulation of data. Creating a list in Dart can be done in several ways. The simplest method is using list literals, where you directly define the elements within square brackets. For example, list int numbers equals 1, 2, 3 creates a list of integers. Another approach is using the list constructor, which initializes an empty list. This is useful when you plan to add elements later. For instance, list string names equals list creates an empty list of strings. Additionally, the list filled method allows you to initialize a list with a specific number of elements, all set to a default value. This is handy when you need a list of a certain size, like list int zeros equals list filled 5, 0, which creates a list of 5 zeros. Each method has its use case, and understanding them helps in efficiently managing data structures. Once a list is created, there are several operations you can perform to manipulate its contents. To add elements, you can use the add method which appends an item to the end of the list, or insert, which places an item at a specific index. For example, numbers add 4 adds 4 to the end of the list, while numbers insert 0. 0 inserts 0 at the beginning. Removing elements can be done with remove to delete a specific value, or remove at to delete an element at a particular position. Accessing elements is straightforward using the index, like numbers 2 to retrieve the third item. Checking the size of a list is essential for avoiding errors, so methods like length return the number of elements, while is empty and is not empty help determine if the list is empty or not. These operations make lists versatile for dynamic data handling. Dart provides a range of powerful methods to work with lists beyond basic operations. The map method allows you to transform each element in the list. For example, numbers map an equals n2 doubles each number. The where method filters elements based on a condition, such as numbers, where an equals n2 to get numbers greater than 2. First where is useful for finding the first element that meets a specific criterion, like numbers. First where an equals n equals 3. Sorting a list can be done with sort, which arranges elements in ascending order, and join combines all elements into a single string, separated by a specified delimiter. These methods enhance the flexibility of lists, enabling complex data transformations and queries. Maps in Dart are created using similar techniques to lists. Map literals are the most common method, where you define key-value pairs within curly braces. For example, map string int ages equals Alice, 25, Bob, 30 creates a map of names to ages. The map constructor initializes an empty map, which can be populated later. This is useful when you need to build a map dynamically. Another method is mapFrom, which creates a new map by copying an existing one. For instance, map string info equals map fromages copies the ages map. Maps are particularly useful for scenarios where data needs to be retrieved using a unique key, such as looking up user details by an ID or storing configuration settings. Managing a map involves adding, removing, and accessing key-value pairs. To add or update an entry, you can use the syntax mapkey equals value, which either creates a new entry or updates an existing one. Removing an entry is done with removeKey, which deletes the specified key and its corresponding value. Checking if a key or value exists in the map is essential for avoiding errors. So methods like contains kiki and contains value are used. Accessing values is straightforward with mapkey, which returns the value associated with the given key. These operations make maps efficient for handling associative data, where each piece of data is linked to a unique identifier. In addition to basic operations, maps offer several methods for advanced data manipulation. The map method transforms each key value pair, similar to the list map method, but for maps. The where method filters key value pairs based on a condition, allowing you to extract specific data. Iterating over keys or values is possible with keys and values, which return iterable collections. For example, map keys gives all the keys, while map values provides all the values. The entries property allows you to access all key value pairs as a list, making it easier to loop through them. These methods make maps powerful tools for processing and analyzing structured data. Understanding the differences between lists and maps is crucial for choosing the right data structure. Lists are ordered and indexed, meaning the position of each element matters. They are ideal for sequences like a list of tasks or a series of numbers. Maps, on the other hand, are unordered and rely on keys for data retrieval. They are best suited for scenarios where you need to look up data using a unique identifier, such as a dictionary or a database. While lists are great for collections of similar items, maps excel at managing structured data with relationships. Knowing when to use each ensures your code is efficient and readable, allowing you to handle complex data scenarios with ease. In conclusion, lists and maps are indispensable components of the Dart programming language, providing the foundation for managing and organizing data in applications. Mastering their operations not only improves code efficiency, but also enhances the ability to solve real-world problems. Practicing with examples, such as building a to-do list or a contact manager, helps solidify understanding and build confidence. By applying these structures effectively, developers can create dynamic and scalable applications that handle data with precision and flexibility. Whether working on small projects or large systems, the ability to leverage lists and maps is a key skill for any Dart programmer. Object-oriented programming is a fundamental approach to software development that organizes code around objects and classes. This paradigm allows developers to model real-world entities by bundling data and functionality into cohesive units. The four key principles that define object-oriented programming are encapsulation, which focuses on restricting direct access to an object's internal state; inheritance, that enables new classes to build upon existing ones; polymorphism, which allows objects to take many forms; and abstraction, that simplifies complex systems by hiding unnecessary details. Dart, as a modern programming language, fully supports these principles through its robust class system and object-oriented features. This approach promotes code reusability, maintainability, and scalability, which are essential for building large-scale applications. A class serves as a blueprint or template for creating objects. It defines the structure and behavior that objects of that class will possess. When we create an instance of a class, we refer to it as an object. For example, if we define a class called dog, we can then create multiple dog objects, each with their own unique characteristics. In Dart, the syntax for creating a class is straightforward. We use the keyword class followed by the class name and a pair of curly braces. To create an object, we simply call the class name as if it were a function. This process of instantiating a class into an object is fundamental to object-oriented programming. Every class has properties and methods that define its characteristics and actions. Properties, also known as fields, are variables that store data specific to an object. Methods are functions that define the behaviors or operations that an object can perform. For instance, in a car class, we might have a property called color to store the vehicle's color, and a method called start engine to simulate starting the engine. These elements work together to make objects dynamic and interactive. By organizing data and functionality within a class, we can create more modular and manageable code structures. Inheritance is a powerful mechanism that allows one class to inherit properties and methods from another class. This promotes code reuse and establishes a hierarchical relationship between classes. In Dart, we use the extends keyword to create an inheritance relationship. For example, a vehicle class might have a method called move, and a bike class that extends vehicle would automatically inherit this method. This means we can add new features to the bike class while retaining all the functionality of the vehicle class. Inheritance helps reduce redundancy and makes code more efficient and easier to maintain. Encapsulation is the practice of hiding an object's internal state and requiring all interaction to occur through well-defined interfaces. In Dart, we achieve encapsulation by using private fields, which are denoted by a leading underscore. These fields cannot be accessed directly from outside the class. Instead, we provide getter and setter methods to control access to the data. For example, a person class might have a private field called name, with a getter to retrieve the name and a setter to update it. This approach ensures data integrity and prevents unintended modifications. Polymorphism allows objects of different classes to be treated as objects of a common superclass. This is particularly useful when we want to write code that can work with objects of various types. In Dart, polymorphism is achieved through method overriding, where a subclass provides a specific implementation of a method defined in its superclass. For instance, an animal class might have a speak method, and a dog subclass can override this method to produce a different sound. This flexibility enables more versatile and extensible code structures. Constructors are special methods used to initialize objects when they are created. Dart provides several types of constructors to handle different initialization scenarios. The default constructor is automatically generated if no other constructor is defined. Named constructors allow us to create multiple ways to instantiate a class. For example, a point class might have a default constructor that takes X and Y values, and a named constructor called 0 that initializes the coordinates to 0. Initializing constructors also allow us to set up the object's state in a clear and concise manner. Dart's object-oriented programming features offer a structured and efficient way to develop applications. By mastering classes, objects, inheritance, encapsulation, and polymorphism, developers can create well-organized and maintainable code. These concepts enable the creation of reusable components that can be easily extended and modified. Practicing these principles through hands-on coding exercises will help solidify understanding and improve overall programming skills. As you continue your journey with Dart, remember that a strong foundation in object-oriented programming is essential for building complex and scalable applications. Classes in Dart serve as blueprints for creating objects, much like how a blueprint outlines the structure of a building. Each class defines the properties, and behaviors that objects of that class will have. Objects are specific instances of these classes, containing their own unique data and actions. Dart fully supports object-oriented programming, which means you can structure your code around classes and objects to model real-world entities. By encapsulating data and functions within a class, you can create organized and reusable code that is easier to manage and understand. To define a class in Dart, you use the keyword class followed by the class name. For example, the class car has properties like model and year, which are variables that store data. These properties and any functions that operate on that data are enclosed within curly braces. This structure allows you to group related data and functionality together, making your code more modular. By defining a class, you create a template that can be used to generate multiple objects, each with its own values for the properties. Creating an object from a class involves using the class name followed by parentheses. This process is called instantiation, and it allocates memory for the object. For instance, the line car my car equals car creates a new instance of the car class. Once an object is created, you can access its properties and methods to interact with the data and perform actions. This allows you to work with specific instances of a class, tailoring their behavior and data to fit different scenarios within your application. Properties in a class are variables that hold the state of an object, such as the breed of a dog. Methods, on the other hand, are functions that define the actions an object can perform, like the bark method in the dog class. These methods can manipulate the object's properties or interact with other parts of the program. For example, the bark method might print a message to the console, demonstrating how the dog object can exhibit behavior. By combining properties and methods, you can create rich, interactive objects that model complex, real-world relationships. Constructors in Dart are special methods used to initialize objects when they are created. The default constructor, which has no parameters, is automatically provided if you don't define one. However, you can also create custom constructors to set initial values for the object's properties. For instance, the person class uses a constructor that takes a name parameter and assigns it to the name property. This allows you to create objects with specific data right from the start, ensuring they are ready to use without additional setup. Dart uses underscores to indicate private members, which are accessible only within the class or library they are defined in. For example, a variable like secret is private and cannot be accessed from outside the class. Public members, such as name, are available to any code that uses the class. This distinction helps protect data from unintended modifications and ensures that only necessary parts of a class are exposed. By using access modifiers, you can control how your classes interact with other parts of your program, improving security and maintainability. Let's consider a real-world example with the student class. This class might have properties like name and roll number to store student details. A method called displayInfo could print these details, making it easy to view the information in an application. For instance, a school management system might use this class to organize student data, allowing teachers to quickly retrieve and display student information. This approach keeps related data and actions together, making the code more intuitive and easier to scale as the application grows. In conclusion, classes and objects are essential to object-oriented programming in Dart, providing a structured way to model and manage data. They promote code reusability by allowing you to create multiple instances of a class with shared functionality. By organizing code into classes, you can achieve better modularity and clarity, making it easier to maintain and expand your programs. Practicing how to define classes, create objects, and use constructors will help you build robust applications. Additionally, mastering access modifiers ensures that your data remains secure and your code remains clean and efficient. Inheritance is a fundamental concept in object-oriented programming that allows one class to inherit properties and methods from another class. This mechanism promotes code reuse and creates a hierarchical structure among classes. In Dart, we achieve inheritance using the extends keyword. The class that provides the properties and methods is called the superclass, while the class that inherits them is referred to as the subclass. For example, if we have a class called Animal, we can create a subclass named Dog that extends Animal. This means Dog will have access to all the features of Animal, and we can add or modify behaviors specific to Dog. The benefits of inheritance are significant in software development. First, it allows us to reuse code, which saves time and reduces redundancy. Instead of writing the same code in multiple places, we can define it once in a superclass and share it across subclasses. Second, inheritance improves code organization by grouping related classes into a hierarchy. This makes the code base easier to maintain and understand. For instance, a vehicle class can serve as a parent for car, which in turn can have subclasses like SUV or sedan. Finally, changes made to a superclass automatically propagate to all subclasses, making updates more efficient and reducing the risk of errors. Polymorphism is another core principle of object-oriented programming that allows objects of different classes to be treated as objects of a common superclass. This means a single interface can represent multiple types of data. Polymorphism is achieved through method overriding, where a subclass provides a specific implementation of a method already defined in its superclass. For example, if we have a shape class with a draw method, subclasses like circle and square can override this method to draw their unique shapes. This flexibility enables methods to behave differently based on the object they are called on, making the code more adaptable and dynamic. Method overriding in Dart allows a subclass to provide a specific implementation of a method that is already defined in its superclass. This is particularly useful when we want to customize or extend the behavior of a method. To explicitly override a method, we use the @override annotation, which helps prevent errors and improves code clarity. For instance, the animal class might have a speak method that prints animal sound, but the dog class can override this method to print woof instead. This ensures that when we call speak on a dog object, it produces the correct output. Overriding is a powerful tool for tailoring class behavior while maintaining a consistent interface. The super keyword in Dart is used to refer to the immediate superclass of a class. It is essential for accessing the superclass's methods and constructors. For example, if a subclass needs to call a constructor from its superclass, we use super followed by the constructor parameters. Similarly, when overriding a method, we can call the superclass's version of the method using supermethod name. This ensures that the subclass can extend the functionality of the superclass without completely replacing it. The super keyword is crucial for maintaining a clear and organized flow of execution in hierarchical class structures. Polymorphism in action demonstrates how a superclass reference can point to a subclass object. This allows us to treat different objects uniformly through a common interface. For example, if we have an animal reference pointing to a dog object, calling the speak method on that reference will execute the dog's implementation of speak. This behavior is determined at runtime, enabling dynamic and flexible code. Polymorphism is especially useful in scenarios where we need to handle multiple types of objects in a consistent way, such as processing a list of shape objects that can be circle, square, or other derived types. Abstract classes and interfaces play a vital role in defining contracts for classes in Dart. An abstract class is a class that cannot be instantiated directly and is used to provide a common structure for its subclasses. It can contain both abstract methods, which have no implementation, and concrete methods, which do. Interfaces in Dart are implemented using abstract classes, and they enforce a set of methods that a class must implement. For example, an abstract class shape might declare a draw method that all subclasses like circle and square must implement. This ensures consistency and allows for polymorphic behavior across different classes. Inheritance and polymorphism are closely related but serve different purposes. Inheritance establishes a relationship between classes where a subclass inherits properties and methods from a superclass. This forms a parent-child hierarchy that promotes code reuse. Polymorphism, on the other hand, is about the ability to use a single interface to represent multiple types of data. Inheritance enables polymorphism by allowing subclasses to override methods, which then behave differently based on the object's actual type. Together, these concepts allow for flexible, scalable, and maintainable code structures. When working with inheritance and polymorphism, it's important to follow best practices to ensure clean and efficient code. First, use inheritance for is a relationships, such as dog is an animal, to maintain logical hierarchies. Avoid creating deep or overly complex inheritance chains, as they can become difficult to manage and debug. Leverage polymorphism to write flexible code that can handle different object types through a common interface. Always use the @override annotation when overriding methods to make the code more readable and prevent accidental overrides. These practices help create well-structured and maintainable Dart applications. In conclusion, inheritance and polymorphism are essential concepts in object-oriented programming with Dart. Inheritance allows classes to share code and form hierarchical relationships, promoting reusability and organization. Polymorphism enables dynamic behavior by allowing objects to be treated as instances of their superclass. Together, these principles enhance code design, making it more scalable and easier to maintain. By practicing inheritance and method overriding in real-world scenarios, developers can build robust and efficient applications that adapt to changing requirements. Dart provides essential libraries for common tasks that developers encounter daily. These libraries are designed to streamline the coding process by offering pre-built functionalities, which means you don't have to reinvent the wheel for every project. By leveraging these libraries, you can focus more on solving unique problems rather than implementing basic operations. The core libraries include Dart Core for fundamental types, Dart Math for mathematical operations, Dart Collection for advanced data structures, Dart I/O for input and output tasks, and Dart Async for handling asynchronous programming. Together, they form the backbone of Dart's capabilities, making it a powerful tool for building applications across different platforms. The Dart Core Library is the foundation of Dart's type system and includes basic types such as string, int, double, bool, null, and dynamic. These types are essential for almost every line of code written in Dart. For example, the string type allows for text manipulation, while int and double handle numerical data. The library also includes utility functions that make tasks like converting between types, checking if a string is empty, or comparing values straightforward. Functions like toStringHelp in converting objects to readable text, isNotEmpty checks if a collection has elements, and compareToAllows for ordering of values. These utilities are critical for ensuring code clarity and reducing errors, especially with Dart's emphasis on null safety. The Dart Math Library is a treasure trove for developers working with numerical computations. It includes constants like pi, which is approximately 3.14159, and e, which is approximately 2.71828. These constants are invaluable for calculations in geometry, physics, and engineering. The The library also provides functions for trigonometry, such as sine and cosine, which are used to calculate angles and distances. For exponentiation, you can use the power function. And for generating random numbers, the random class offers methods like nextInt to produce integers within a specified range. These tools are essential for applications that require mathematical precision, from game development to scientific simulations. The Dart Collection Library extends Dart's capabilities by introducing advanced data structures like list, map, set, and queue. These structures allow for efficient storage and manipulation of collections of data. For instance, a list can hold an ordered sequence of elements, while a map stores key-value pairs. The library also includes utility classes that make operations like sorting, filtering, and transforming data much easier. Functions like listGenerate can create dynamic lists based on a function. MapFrom copies a map's contents, and setCast ensures type safety when working with sets. These features are crucial for managing complex data interactions in applications, making code more organized and efficient. The Dart I/O library is essential for applications that need to interact with the file system, network, or other system resources. It provides classes for reading from and writing to files, which is fundamental for tasks like saving user data or loading configuration files. For network communication, the library includes HTTP client for making HTTP requests, allowing applications to fetch data from the internet. Additionally, it offers tools for managing directories and processes, such as retrieving the current working directory. These capabilities are vital for building applications that require persistent storage, real-time data updates, or integration with external services. The library's stream-based approach also enables handling large data transfers efficiently. The Dart Async library is the cornerstone of asynchronous programming in Dart, enabling non-blocking operations that keep applications responsive. It introduces futures, which represent values that may be available now or later, and streams, which handle sequences of events over time. This is particularly useful for tasks like fetching data from a server or processing user input without freezing the UI. The library includes utilities like future delayed to pause execution for a specified time, stream, from iterable to create streams from collections, and the await keyword to simplify asynchronous code. By mastering these tools, developers can create smooth, efficient applications that handle complex operations without sacrificing performance. Dart's built-in libraries are critical for efficient development, as they provide ready-to-use solutions for a wide range of tasks. By mastering these libraries, developers can reduce the amount of boilerplate code needed, leading to faster development cycles and more maintainable applications. These tools also enhance productivity by allowing developers to focus on business logic rather than implementing basic functionalities. As you practice using these libraries, you'll gain the ability to build robust and scalable applications that leverage Dart's full potential. Whether you're working on mobile, web, or desktop projects, these libraries will be your foundation for creating high-quality software. Today, we will explore the fundamentals of strings and numbers in the Dart programming language. These two data types are essential for handling text and performing calculations, which are core to almost every application. Understanding how to manipulate strings and work with numbers allows us to process user input, generate dynamic content, and perform complex computations. We will dive into the key concepts of operations, methods, and conversions that will empower you to work effectively with these types. Let's start with string operations. One of the most common tasks is concatenation, which involves joining two or more strings together. In Dart, we use the plus operator to achieve this. For example, hello plus world results in hello world. Another powerful feature is string interpolation, which allows us to embed variables directly within a string. For instance, if we have a variable x with the value 42, writing value x will produce value 42. When comparing strings, we can use the equality operator to check if they are identical, or the not equal to operator for the opposite. Additionally, the compare to method helps determine the lexicographical order of two strings, returning a negative, 0, or positive value based on their order. Now let's look at the methods available for strings. The length property gives the number of characters in a string, such as Dart, length returning 4. The substring method allows us to extract a portion of a string. For example, Dart, substring 0, 2 gives us duh. To modify the case of characters, we can use to uppercase and to lowercase, transforming Dart into Dart, or dart back into dart. The replace all method is useful for replacing all occurrences of a specific character or substring, like changing dart to dort by replacing a with o. Finally, the trim method removes any leading or trailing white space, so dart becomes dart. These methods are invaluable for processing and formatting text in applications. Dart offers several number types to handle different kinds of numerical data. The int type represents whole numbers, such as 42 or -100, and is used for scenarios where fractional values are not needed. The double type, on the other hand, handles floating point numbers like 3.14 or 2.5e5, which are useful for precise calculations. Both int and double are subclasses of the num type, which acts as a common base class. This means that any variable declared as num can hold either an int or a double, providing flexibility in certain situations. However, for specific operations, it's often better to use the more precise int or double types. When working with numbers, we perform various operations. Arithmetic operators such as plus, minus, multiplication, division, and modulus allow us to carry out calculations. For example, 5 plus 3 equals 8, while 10 minus 4 equals 6. Increment and decrement operators, like x plus plus or x minus minus, are shorthand for increasing or decreasing a value by 1. Type conversion is another critical aspect, as it enables us to switch between data types. For instance, converting a string to an integer using int parse, or a number to a string with toString. These operations are essential for handling user input and ensuring data compatibility. Type conversion is a vital skill when working with numbers and strings. For example, int parse 123 converts the string 123 into the integer 123, while 42 to string turns the number 42 into the string 42. However, invalid inputs can cause errors, such as parsing a non-numeric string. To handle such cases gracefully, we use try-catch blocks, which allow our programs to catch exceptions and prevent crashes. This ensures that our applications remain robust and user-friendly, even when unexpected data is encountered. In conclusion, we have covered the essential aspects of string manipulation and number operations in Dart. By mastering these concepts, you can build dynamic and functional applications. I encourage you to practice by creating a simple calculator that handles both strings and numbers. Don't hesitate to ask questions if anything is unclear. These foundational skills will serve as a strong base for more advanced topics in Dart programming. Error handling is a fundamental aspect of building reliable Dart applications. Without proper error handling, even minor issues can cause your app to crash unexpectedly, leading to a poor user experience. By implementing robust error handling strategies, you can anticipate and manage errors gracefully, ensuring your application remains stable. Key concepts in Dart error handling include exceptions, which are objects that represent errors, the try-catch block, which allows you to execute code and catch exceptions, and error propagation, which involves passing errors up the call stack for appropriate handling. These tools work together to create resilient software that can recover from unexpected situations. The try-catch block is one of the most essential tools for managing exceptions in Dart. When you wrap code in a try block, you are telling the Dart runtime to monitor that code for any exceptions. If an exception occurs, the catch block intercepts it, preventing the program from terminating abruptly. For example, if a function attempts to divide by 0 or access a null variable, the try-catch structure ensures that the error is handled without crashing the application. This mechanism is crucial for maintaining control over your program's flow and providing meaningful feedback to users or developers. The throw keyword allows you to explicitly raise exceptions in your Dart code. This is particularly useful when you detect invalid states or conditions that should not occur during normal execution. For instance, if a function expects a positive number but receives a negative value, you can throw an exception to signal the problem. Dart supports throwing strings, objects, or custom exception classes, giving you flexibility in how you represent errors. By using throw, you can enforce constraints and make your code more predictable, ensuring that invalid operations are flagged early. When handling exceptions, the rethrow keyword is invaluable for preserving the original context of an error. Unlike simply catching an exception and ignoring it, rethrowing allows the error to propagate to the caller, maintaining the stack trace that helps identify where the issue originated. This is especially useful when you need to log the error or perform some cleanup before passing it along. For example, if a function catches an exception to record it in a log file. Rethrowing ensures that the original error is not lost, making debugging more efficient and accurate. The finally block ensures that specific code runs regardless of whether an exception occurs. This is critical for tasks like closing files, releasing resources, or resetting states, which must happen even if an error is thrown. For instance, if you open a file in a try block, the finally block can guarantee that the file is closed properly, preventing resource leaks. The finally block executes after the try and catch blocks, making it the ideal place for cleanup operations that are essential for maintaining the integrity of your application. Creating custom exception classes allows you to define specific error types that are meaningful to your application. By implementing the exception class, you can encapsulate error details and make your code more readable. For example, a custom invalid input exception can be thrown when a user enters incorrect data, making it easier to identify and handle such cases. Custom exceptions improve error categorization, enabling more precise error handling and making your code base easier to maintain and debug. Following best practices for error handling ensures your code is both robust and maintainable. One key principle is to handle exceptions at the appropriate level, avoiding overly broad catch blocks that might mask unexpected errors. Always log or notify users when an exception occurs, as empty catch blocks can hide critical issues. Using the on keyword allows you to catch specific exception types, ensuring that your error handling is targeted and efficient. Finally, testing error scenarios thoroughly helps uncover potential issues before they affect end users, leading to more reliable and trustworthy applications. In conclusion, effective error handling is a cornerstone of stable and user-friendly Dart applications. By mastering try-catch blocks, the throw keyword, and custom exceptions, you can create code that gracefully handles unexpected situations. Adhering to best practices ensures that your error handling is both efficient and maintainable, while prioritizing user experience means providing clear feedback and preventing crashes. With these strategies, you can build applications that are not only functional, but also resilient in the face of errors. Asynchronous programming is a fundamental concept in modern software development that allows tasks to run without blocking the main execution flow. This approach ensures that your application remains responsive and efficient, especially when dealing with time-consuming operations. In Dart, we use a construct called futures to manage these asynchronous tasks. Futures act as placeholders for values that will be available later, enabling you to perform other operations while waiting for the result. The benefits of using asynchronous programming include improved performance, as it prevents the application from freezing during long operations. It also enhances responsiveness, making the user experience smoother, and supports scalability by handling multiple tasks concurrently. Common scenarios where asynchronous programming shines include making API calls to fetch data from the internet, performing file input and output operations, and managing timers or delayed actions. A future in Dart is a core concept that represents a value that may not be available immediately. Think of it as a promise that a result will be delivered at some point in the future. This placeholder allows your code to continue executing other tasks while waiting for the result. Futures can exist in one of three states. The first is uncompleted, which means the operation is still in progress and the result is not yet available. The second state is completed with a value, indicating that the asynchronous operation has successfully returned a result. The third state is completed with an error, which occurs when the operation encounters a problem and cannot proceed. Understanding these states helps you design robust applications that handle both success and failure scenarios gracefully. Creating a future in Dart can be done in several ways. The most straightforward method is using the future constructor, which allows you to define an asynchronous operation. For example, the code future delayed duration seconds 2 equals done creates a future that completes after a 2-second delay. This is useful for simulating delays or scheduling tasks. Another approach is using the future value method, which immediately completes a future with a specific value. This is handy when you want to wrap a synchronous value into a future for consistency. Similarly, the future error method allows you to create a future that immediately completes with an error, which is useful for testing or handling exceptional cases. These methods provide flexibility in how you structure your asynchronous code. The async and await keywords are powerful tools in Dart that simplify asynchronous programming. When you mark a function as async, it automatically returns a future, making it easier to work with asynchronous operations. The await keyword pauses the execution of the function until the future completes, allowing you to write code that looks and behaves like synchronous code. For example, in the function fetch data, the await keyword is used to wait for the result of fetch data from API. Once the data is retrieved, it is printed to the console. This approach makes the code more readable and easier to debug, as it avoids the complexity of nested callbacks or chained then calls. Using async await is a best practice for writing clean and maintainable asynchronous code. In addition to async await, Dart provides the then method to handle the results of a future. The then method allows you to specify a callback that executes once the future completes successfully. For instance, calling fetch data, then data, print data, data will print the retrieved data. This method is particularly useful for chaining multiple operations, where the result of one future is used as input for another. By chaining then calls, you can create a sequence of asynchronous steps that execute in order. However, it's important to note that while then is effective, it can lead to callback hell if not managed carefully. This is where async await often provides a more structured and readable alternative. Error handling is a critical aspect of working with futures. The catch error method allows you to catch and handle errors that occur during the execution of a future. For example, calling fetch data, catch error, print error ensures that any errors are logged and do not crash the application. This method is especially useful when you want to provide a fallback or recovery mechanism. Additionally, you can use the onError parameter in the then method to handle specific types of errors. This level of control ensures that your application can gracefully handle unexpected situations, improving reliability and user experience. Combining catch error with on-error handling allows you to create robust error management strategies tailored to your application's needs. When working with multiple asynchronous tasks, Dart provides utilities like FutureWait and FutureAny to manage them efficiently. The FutureWait method takes a list of futures and returns a new future that completes only when all the provided futures have completed. This is ideal for scenarios where you need the results of multiple operations before proceeding, such as fetching data from multiple APIs. On the other hand, FutureAny returns the first future that completes, which is useful when you only need the result of the first successful operation, such as choosing the fastest API response. These methods allow you to coordinate complex asynchronous workflows, ensuring that your code remains efficient and scalable. By leveraging these tools, you can handle parallel tasks with ease. Adhering to best practices when working with futures ensures that your code is maintainable, readable, and efficient. One key practice is to avoid nested await statements, as they can make the code harder to follow. Instead, structure your code to keep the flow linear. Using try-catch blocks with await provides a structured way to handle errors, making it easier to debug and manage exceptions. Keeping asynchronous code modular by breaking it into smaller, reusable functions improves maintainability and testability. While the then method is useful, prefer using async await for clarity, as it reduces the complexity of nested callbacks. These practices help create a more robust and scalable application, making it easier to manage asynchronous operations as your project grows. In summary, futures are essential for handling asynchronous tasks in Dart, enabling your applications to perform non-blocking operations efficiently. The async await syntax simplifies the writing of asynchronous code, making it more readable and easier to manage. Proper error handling ensures that your applications can recover from unexpected issues, leading to a more reliable user experience. By combining multiple futures, you can manage complex workflows and coordinate parallel tasks effectively. As you continue developing with Dart, mastering these concepts will allow you to build high-performance, responsive, and scalable applications that meet modern development standards. Async await is a fundamental feature in the Dart programming language that allows developers to handle asynchronous operations more efficiently. Unlike traditional callback-based approaches, this syntax makes asynchronous code feel more like synchronous code, which is easier to read and maintain. It is particularly useful for tasks such as making API calls, reading from or writing to files, and querying databases. By using async await, developers can write cleaner code that avoids the complexities of nested callbacks, making it a powerful tool for building responsive applications. The basic syntax of async await involves two key keywords. The async keyword is used to declare a function as asynchronous, which means it returns a future. The The await keyword is used within an async function to pause the execution of the function until a future completes. For example, when you call a function that returns a future, using await allows you to work with the result as if it were a regular value. This structure simplifies the flow of asynchronous code, making it more intuitive and easier to debug. One of the primary benefits of using async await is improved code readability. By eliminating the need for nested callback functions, it reduces the risk of callback hell, which can make code difficult to follow. Additionally, error handling becomes more straightforward with try-catch blocks, allowing developers to handle exceptions in a more structured way. This leads to more maintainable code, as the logic is linear and easier to trace compared to traditional asynchronous patterns. To understand async await, it is essential to grasp three core concepts. A future represents a value that may be available immediately or at some point in the future, acting as a placeholder for the result of an asynchronous operation. The async keyword marks a function as returning a future, enabling the use of await within it. The await keyword suspends the execution of the function until the future is resolved, allowing the program to continue with other tasks in the meantime. Together, these elements form the foundation of asynchronous programming in Dart. An example of using async await is fetching data from an API. In this scenario, a function like fetch user data would use the HTTP package to send a request. The await keyword is used to pause the function until the response is received, after which the data is processed and returned. This approach ensures that the application remains responsive, as the asynchronous operation does not block the main thread. Such patterns are common in real-world applications where network requests are frequent. Error handling in async functions is made simpler with try-catch blocks. When an exception occurs during an asynchronous operation, the try block captures it, and the catch block handles it appropriately. For instance, if a network request fails, the catch block can log the error or display a user-friendly message. This structured approach to error handling makes it easier to manage unexpected issues, improving the reliability and robustness of the application. Async code differs from synchronous code in how it handles execution. Synchronous operations block the thread until they complete, which can lead to unresponsive applications. In contrast, async code allows the program to continue executing other tasks while waiting for a future to complete. For example, a heavy computation in a synchronous function would freeze the app, but using an async version with a wait lets the app remain responsive. This distinction is crucial for building efficient and user-friendly applications. When using async await, there are several best practices to follow. Avoid using await in loops, as it can lead to inefficient code. Instead, use future wait to execute multiple asynchronous tasks concurrently. Also, reserve async await for I/O-bound operations, such as network requests or file access, rather than CPU-intensive tasks, which may require alternative approaches like isolates. Always include error handling with try-catch to ensure the application can recover from unexpected issues. Common mistakes when working with async await include forgetting to mark a function as async, which leads to errors when using await inside it. Another mistake is using await without a future return type, which can cause runtime exceptions. Additionally, neglecting to handle exceptions properly can result in uncaught errors that crash the application. By being mindful of these pitfalls, developers can write more reliable and efficient code. In conclusion, async await is a powerful feature in Dart that simplifies asynchronous programming. It enhances code readability by making asynchronous operations feel more like synchronous ones, reduces the complexity of nested callbacks, and improves error handling. By mastering this feature, developers can build responsive and efficient applications that provide a better user experience. It is an essential tool for any Dart developer looking to create modern, scalable software. Dart's null safety is a powerful feature designed to prevent null reference errors that can occur during runtime. By introducing non-nullable and nullable types, it helps developers write more reliable code. Non-nullable types ensure that variables cannot hold null values, which reduces the risk of unexpected crashes. Nullable types, on the other hand, allow variables to explicitly accept null values, giving developers more flexibility. Dart offers two modes for null safety. Sound mode, which enforces strict null checks and ensures type safety, and legacy mode, which is the older approach without these safeguards. Understanding these modes is essential for modern Dart development. In Dart, variables are non-nullable by default, meaning they cannot hold null values unless explicitly declared otherwise. For example, if you declare an integer variable like int x equals 5, ensures that X will never be null. Attempting to assign null to such a variable will result in a compilation error, which helps catch potential issues early. This approach encourages safer coding practices by forcing developers to handle null values intentionally. By making nullability explicit, Dart reduces the likelihood of runtime errors and improves code quality. When a variable needs to accept null values, Dart allows you to use the question mark symbol to declare a nullable type. For instance, int x equals null means that x can hold either an integer or a null value. This explicit declaration makes it clear to other developers that the variable might be null, promoting better code readability. Nullable types are especially useful in scenarios where data might be missing or optional. By using this feature, developers can handle null values more gracefully, reducing the chances of runtime crashes caused by unexpected nulls. Dart provides several null-aware operators to simplify handling null values in code. The null-aware access operator allows you to safely access properties or methods of an object that might be null. For example, name. Length will return the length of name if it is not null. Otherwise, it returns null. The null coalescing operator lets you provide a default value if the expression on its left is null. For instance, name guessed ensures that name has a value even if it was initially null. The null-aware assignment operator equals assigns a value to a variable only if it is currently null. These operators make null handling more concise and less error-prone. The late keyword in Dart is used to declare variables that will be initialized later, but are guaranteed to have a value before they are used. For example, late int x tells the compiler that x will be assigned a value before it is accessed. This is useful in cases where initialization happens after declaration, such as in asynchronous operations, or when the value is determined at runtime. However, using late requires careful management because if the variable is accessed before it is initialized, it will cause a runtime error. It is a trade-off between flexibility and safety, best used when you are certain about the timing of initialization. In practice, understanding the difference between nullable and non-nullable variables is crucial. For example, string name equals null indicates that name can be null, while string name equals Alice ensures that name will always have a value. When working with nullable variables, it is common to use conditional checks like if name, null to handle cases where the value might be missing. Additionally, the null assertion operator can be used to force a non-null value. But this should be done with caution, as it can lead to runtime errors if the value is actually null. Tools like Dart Fix can help automate the process of updating legacy code to use null safety effectively. Common errors in Dart often stem from null references, uninitialized variables, or type mismatches. To address null reference errors, developers should use null-aware operators or perform explicit null checks. For uninitialized variables, using the late keyword or initializing them with default values can prevent runtime issues. Type mismatches can be resolved by ensuring that variables are declared with the correct nullability. The Dart compiler provides warnings and suggestions to help identify and fix these issues, making it easier to write robust code. By addressing these errors proactively, developers can significantly improve the reliability of their applications. Adhering to best practices for null safety is essential for writing clean and maintainable Dart code. Start by using non-nullable types by default, as this reduces the risk of null-related errors. Use the question mark symbol to declare nullable types when necessary, and avoid the null assertion operator unless you are absolutely certain the value is not null. The late keyword can be useful for delayed initialization, but it should be used judiciously. Regularly updating code to adopt sound null safety ensures long-term stability. Finally, testing scenarios where variables might be null helps uncover edge cases and strengthens the overall quality of the code base. Null safety is a fundamental aspect of modern Dart development, significantly improving code reliability and reducing runtime errors. By understanding and applying nullability concepts, developers can write more predictable and robust applications. It is crucial to follow best practices, such as preferring non-nullable types and using null-aware operators effectively. Practicing with real-world examples helps reinforce these concepts and builds confidence in handling null values. As Dart continues to evolve, mastering null safety will remain a key skill for any developer aiming to create high-quality, error-free code. Dart packages are reusable code modules that extend the functionality of your applications. Think of them as pre-built tools, libraries, and utilities that you can incorporate into your projects. These packages help streamline development by reducing the need to write code from scratch. For example, instead of building an HTTP client yourself, you can use the HTTP package to handle network requests. Dart packages can be either public, which means they are hosted on pub, dev for anyone to use, or private, designed for internal use within an organization. Managing these packages is done through the pub toolchain, which is the standard tool for dependency management in the Dart ecosystem. This tool helps you fetch, update, and organize packages seamlessly. PubDev is the official repository for Dart packages, serving as a central hub where developers can discover, share, and utilize a vast collection of packages. It hosts thousands of packages tailored for Flutter, Dart, and web development, making it a go-to resource for developers. Whether you need a package for state management, data parsing, or UI components, PubDev is likely to have it. The platform allows developers to search for packages by name, functionality, or keywords. You can install packages directly into your project and even publish your own creations. PubDev also supports versioning, ensuring that you can track changes and dependencies effectively. Additionally, it manages package metadata, such as descriptions, authors, and licensing information, making it easier for users to understand and trust the packages they use. To add packages to your Dart project, you need to declare them in the pubspec YAML file, which is the configuration file for your project. For instance, you might write dependencies HTTP 0.13.3 to include the HTTP package. The caret symbol here indicates that any version compatible with 0.13.3 up to, but not including 1.0.0, will be used. Once you've updated your pubspec YAML, run the Flutter pub get or Dart pub get command to fetch the dependencies. This command downloads the specified packages and their dependencies, storing them in the pubspec lock file. This file acts as a version lock, ensuring that every developer working on the project uses the same versions of the packages, which helps avoid conflicts and inconsistencies. Package versioning in Dart follows semantic versioning, a system that uses a three-part number like 1, 2, 3. The first number represents major versions, the second minor, and the third patch. This system allows developers to understand the impact of updates. For example, a major version change might include breaking changes, while a patch update fixes bugs without altering functionality. When specifying versions in PubSpec YAML, the caret symbol is used to allow compatible updates. For instance, 1.2.3 means any version from 1.2.3 up to, but not including 2.0.0. If you need more precise control, you can use greater than or less than operators. However, it's important to avoid using the asterisk, as it can lead to unstable dependencies by pulling in any version. Proper version constraints ensure your project remains stable and compatible with the packages it relies on. Once a package is added to your project, you can use it in your code by importing it with the import statement. The syntax for importing a package is import package, package name /. For example, to use the HTTP package, you might write import package http/http dart as HTTP. This allows you to access the package's functions and classes. Packages often provide powerful features, such as APIs for network requests, widgets for UI components, or utilities for data manipulation. To make the most of a package, always refer to its documentation, which typically includes usage examples, API references, and best practices. By leveraging well-documented packages, you can save time and focus on building the unique aspects of your application. Creating a Dart package involves a few key steps. Start by using the pub create package name command, which generates a template for your package. This template includes a lib directory for your code, a PubSpec YAML file for configuration, a README MD file for documentation, and a license file for legal terms. The lib directory is where you define your public APIs, ensuring that other developers can use your package effectively. For example, if you're creating a utility package, you might place your helper functions here. It's important to organize your code cleanly and document it thoroughly. By following this structure, you make it easier for others to understand and integrate your package into their projects. Publishing a Dart package to pub dev requires careful preparation. First, ensure that your PubSpec YAML file contains valid metadata, including a unique name, a version number, and a clear description. The version should follow semantic versioning to communicate the package's stability. Once your package is ready, test it locally to confirm that it works as expected. Then, run the pub publish command to upload it to pub dev. If you need to update the package with major changes, use pub publish force to bypass version checks. However, this should be done cautiously, as it can affect users relying on previous versions. Maintaining up-to-date documentation and providing examples are crucial for helping users understand how to use your package effectively. When working with Dart packages, following best practices ensures reliability and usability. Keep dependencies minimal by only including what's necessary for your package to function. This reduces the risk of conflicts and makes your package easier to maintain. Use version constraints to define acceptable ranges for dependencies, which helps prevent unexpected issues when updates occur. Test your package across different Dart versions and platforms to ensure compatibility. For example, if your package is used in both Flutter and web applications, verify that it works seamlessly in both environments. Lastly, adhere to naming conventions, such as using snakecase for package names, to make your packages easier to discover and understand. These practices contribute to a healthier and more sustainable Dart ecosystem. Dart packages are a powerful tool for enhancing productivity and promoting code reuse. They allow developers to build on existing solutions rather than reinventing the wheel, saving time and effort. Pub Dev serves as the central hub for discovering, managing, and sharing packages, making it an essential resource for the Dart community. Proper versioning and publishing practices ensure that packages remain reliable and up-to-date, fostering trust among users. By practicing the creation and use of packages, you can deepen your understanding of the Dart ecosystem and contribute to its growth. Whether you're using existing packages or creating your own, mastering these concepts will elevate your skills as a Dart developer. File input-output operations are fundamental to building applications that need to store and retrieve data. Whether you're saving user preferences, logging events, or managing large data sets, understanding how to interact with files is essential. Dart provides a robust set of tools for this purpose, primarily through the Dart I/O library. This library allows developers to perform tasks such as creating, reading, updating, and deleting files. Common scenarios where file I/O is critical include saving application configurations, generating reports, or backing up data. By mastering these operations, you can ensure your Dart applications handle data efficiently and reliably. The Dart I/O library is the cornerstone of file operations in Dart. It introduces key classes like file, directory, and file system entity, which represent files, folders, and file system objects respectively. These classes offer methods for creating, reading, writing, and deleting data. For instance, the file class allows you to read or write text or binary data. The library supports both synchronous and asynchronous operations, giving you flexibility based on your application's needs. Synchronous methods like read as string sync are useful for simple tasks, while asynchronous methods like read as string prevent blocking the main thread during I/O operations. This dual approach ensures you can optimize performance and responsiveness in your applications. Reading from files in Dart can be done using methods like read as string for text or read as bytes for binary data. These methods return futures, making them ideal for asynchronous operations. If you need to handle large files or avoid blocking the main thread, asynchronous reading is the way to go. However, for small, quick reads, synchronous methods like read as string sync are straightforward. It's important to handle exceptions, such as when a file is missing or inaccessible. For example, using a try-catch block ensures your application doesn't crash if a file isn't found. Additionally, Dart provides a convenient read as JSON method for parsing JSON files directly, which simplifies working with structured data. Writing to files in Dart is equally straightforward. The write as string method allows you to save text data, while write as bytes handles binary data. If you want to add content to an existing file instead of overwriting it, you can use the file mode append mode. For instance, logging new entries to a file without losing previous data is a common use case. Always remember to close the file after writing to ensure all data is properly saved and resources are released. Using a with statement or explicitly calling close helps prevent resource leaks. A simple example is writing a greeting message to a file, which demonstrates how easily you can persist data in your applications. Data serialization is the process of converting objects into a format that can be stored or transmitted. This is crucial for saving complex data structures, exchanging information between systems, or caching results. Dart supports multiple serialization formats, including JSON, XML, YAML, and binary. The Dart Convert library provides built-in support for JSON, making it one of the most commonly used formats. For custom data types, you need to implement to JSON, and from JSON methods to define how objects should be converted. This allows your application to handle unique data structures while maintaining compatibility with external systems. JSON serialization in Dart is made easy with the JSON encode and JSON decode functions from the Dart convert library. These functions convert Dart objects into JSON strings and vice versa. For example, encoding a map like name Dart produces the string name Dart, which is human readable and widely used. Decoding JSON strings back into Dart objects is equally simple, enabling seamless data exchange. For larger projects, the JSON serializable package automates the generation of to JSON, and from JSON methods, reducing boilerplate code. This is particularly useful when working with complex data models, as it ensures consistency and minimizes errors. Handling binary data in Dart requires the Dart type data library, which provides classes like listInt for storing sequences of bytes. This is essential for working with files such as images, audio, or video. The readAsBytes method retrieves binary data from a file, while writeAsBytes saves it. For structured binary data, you can use Binary Reader and Binary Writer to parse and construct data in a specific format. For example, reading an image file's bytes allows you to manipulate or store it efficiently. Understanding binary handling is crucial for applications that deal with low-level data processing or network protocols requiring precise byte manipulation. Following best practices for file I/O ensures your applications are robust and efficient. Always handle exceptions like file system exception to prevent crashes from unexpected errors. For large files, use asynchronous methods to keep the user interface responsive. Before performing operations, validate file paths and check permissions to avoid runtime errors. Finally, clean up resources by closing files or using with statements, which automatically release system resources. These practices not only improve reliability, but also enhance the user experience by preventing issues like data corruption or memory leaks. In conclusion, file I/O and data serialization are vital for building functional Dart applications. The Dart I/O and Dart convert libraries provide powerful tools to to manage data persistence and exchange. Prioritizing error handling and performance ensures your applications can handle real-world scenarios gracefully. By practicing serialization techniques, you can create systems that communicate effectively with other platforms. Whether you're saving user data or exchanging information, mastering these concepts will elevate the quality and reliability of your Dart projects. Dart is a versatile language that allows developers to create powerful command line applications. These types of applications are crucial for automation tasks, scripting, and building system tools that run without a graphical interface. Dart provides a rich set of libraries, such as Dart.io, which offers functionalities for input and output operations, and additional packages specifically designed to simplify the development of command line interfaces. One of the key advantages of using Dart for CLI applications is its cross-platform support, meaning your tools can run seamlessly on Windows, Mac OS, and Linux. Additionally, Dart's performance is optimized for such tasks, making it a reliable choice for developers who need efficient and scalable solutions. The language also emphasizes ease of use, allowing even beginners to create functional CLI tools quickly. To begin developing Dart CLI applications, the first step is to install the Dart SDK from the official website at Dart.dev. This installation includes the Dart compiler and essential tools like Dart and pub. Once installed, it's important to set up the system's path environment variable so that the Dart and pub commands are accessible from any directory. This setup ensures you can run Dart commands without navigating to the SDK's installation folder. To create a new CLI project, you can use the Dart create command, which generates a template structure with necessary files. For example, running Dart create Mikli app will set up a new project. Once your code is written, you can test it directly using the Dart run command followed by the file name, making the development process efficient and straightforward. The foundation of any Dart CLI application is the main function, which serves as the entry point for execution. This function is defined in a Dart file and typically takes a list of strings as arguments, representing the command line inputs provided when the program runs. For instance, a simple hello Dart CLI program would look like this: void main list string args, print hello Dart CLI. Here, the args parameter allows the program to access any arguments passed during execution. This structure is essential for building applications that can interact with users or other systems through command line inputs. As you progress, you can expand the main function to handle more complex logic, such as parsing user inputs or performing specific tasks based on the provided arguments. Command line arguments are a critical component of CLI applications, enabling users to customize the behavior of a program. Dart provides multiple ways to access and parse these arguments. One approach is to use the platform arguments property from the Dart I/O library, which returns a list of all arguments passed to the program. For example, importing Dart I/O and printing platform arguments will display the arguments as a list. However, for more structured parsing, developers often use the args package, which allows for handling flags, options, and positional arguments with ease. This package supports features like parsing long and short flags, validating input, and providing help messages. By leveraging these tools, you can create CLI applications that respond dynamically to user input, making them more flexible and user-friendly. Handling input and output is fundamental to creating interactive CLI applications. Dart provides the stdin and stdout objects from the Dart I/O library to read from and write to the console. For example, the code print enter your name, string name equals stdin, read line sync, print hello name demonstrates how to prompt the user for input and display a response. This approach is useful for simple interactions, but for more advanced scenarios, you can redirect output to files using the file class. For instance, writing to a file involves creating a file instance and using methods like write_as_string. Similarly, reading from files can be done with read_as_string or other specialized methods. These capabilities make Dart an excellent choice for applications that need to process data from external sources or generate output for further use. Dart offers a variety of packages that enhance the development of CLI applications. The args package is particularly useful for parsing command line arguments, allowing you to define flags, options, and subcommands with minimal code. The logging package provides a robust framework for adding debug messages, warnings, and errors, which is invaluable for troubleshooting. For executing system commands, the process package enables your CLI tool to interact with external programs, making it possible to automate complex workflows. The file package simplifies file I/O operations, while the path package ensures that file paths are handled correctly across different operating systems. Together, these packages provide a comprehensive toolkit for building efficient, maintainable, and cross-platform CLI tools. Once your CLI application is developed, the next step is to build and distribute it. Testing locally can be done using the Dart pub run command, which executes the app without requiring a full build. To create a standalone executable, you can use the Dart compile exe command, which compiles your Dart code into a native binary. This binary can then be distributed to users without requiring them to install the Dart SDK. To manage dependencies and configuration, the pubspec YAML file is essential, as it lists all required packages and their versions. By packaging your application with this file, you ensure that it can be easily installed and run on any system. Finally, distributing the compiled binary as a standalone file allows users to run your tool effortlessly on Windows, Mac OS, or Linux. Advanced CLI applications often require features like subcommands, which allow users to execute different actions within a single tool. For example, a CLI tool might have subcommands such as add, remove, and list, each performing a specific task. This structure is achieved by parsing the command line arguments and routing them to the appropriate functions. Interactive prompts can also enhance user experience by guiding users through complex workflows. For instance, using stdin to ask for input during execution makes the tool more intuitive. Additionally, the Dart I/O library offers advanced I/O operations, such as reading from and writing to files, handling streams, and managing network connections. These capabilities enable the creation of sophisticated CLI tools that can perform a wide range of tasks efficiently. To ensure your CLI applications are robust and maintainable, it's important to follow best practices. First, keep your code modular by breaking it into smaller, reusable functions or classes. This approach makes it easier to test and update individual components. Second, validate all user inputs to prevent errors and ensure the program behaves as expected. For example, checking that required arguments are provided or that input values are of the correct type can prevent crashes. Third, provide clear documentation that explains how to use the tool, including examples of commands and their expected outputs. Finally, test your application thoroughly using DART's testing framework, DART test, and the pub run test command. These practices not only improve the reliability of your tools, but also make them more accessible to other developers and users. DART is a powerful language for building efficient and scalable command line applications. Its extensive libraries and packages provide the tools needed to handle everything from basic I/O operations to complex argument parsing and system interactions. By leveraging these features, developers can create CLI tools that are both functional and user-friendly. Following best practices ensures that your applications are maintainable and adaptable to future requirements. The key to mastering DART CLI development is practice. Building real-world tools like scripts for automation or system utilities will deepen your understanding and improve your skills. As you continue to explore, you'll discover new ways to utilize DART's capabilities to solve problems and streamline workflows. DART's concurrency model is built around a single-threaded, event-driven, and asynchronous approach. This means that DART runs on a single thread, but handles asynchronous operations efficiently through an event loop. The key concepts include the event loop, which manages tasks in a queue, async await syntax that simplifies asynchronous code, isolates that provide parallelism, and streams that handle multiple values over time. Understanding these elements is crucial for building responsive applications that can manage I/O operations, user interactions, and background tasks without blocking the main thread. For example, when a user clicks a button, the event loop ensures that the action is processed without freezing the interface. This model allows developers to write efficient code that scales well with both lightweight and resource-intensive operations. The DART event loop is the core mechanism for handling asynchronous operations. It processes tasks in a specific order, ensuring that the application remains non-blocking. Tasks are divided into microtasks and event tasks. Microtasks, such as those created with future microtask, are executed immediately after the current synchronous code completes. Event tasks, like those from future or timers, are processed in the next iteration of the event loop. This structure allows for efficient management of asynchronous operations without overwhelming the system. For instance, when a network request is made, the event loop cues the task and continues processing other operations until the response is available. This ensures that the application remains responsive even during long-running operations. The async await syntax in Dart transforms how asynchronous code is written. Instead of using nested callbacks or then chains, developers can use the async keyword to mark a function as asynchronous and await to pause execution until a future completes. For example, a function like future void fetch data async allows the code inside to be written in a sequential, readable manner. This approach reduces the complexity of handling asynchronous operations and makes debugging easier. By using async await, developers can create code that is both efficient and maintainable, avoiding the pitfalls of callback hell. This syntax is particularly useful for handling I/O operations, such as fetching data from a server or reading from a file. Isolates in Dart provide a way to achieve true parallelism by running independent memory spaces with their own event loops. Unlike threads in other languages, isolates do not share memory, which prevents data races and ensures thread safety. Communication between isolates occurs through message passing, using methods like send and onMessage. This makes isolates ideal for CPU-intensive tasks, such as processing large datasets or performing complex calculations. For example, a mobile app might use an isolate to handle image processing without freezing the user interface. By leveraging isolates, developers can take full advantage of multi-core processors while maintaining the simplicity of Dart's single-threaded model. Futures and streams are two fundamental tools in Dart for handling asynchronous data. A future represents a single value that will be available at some point in the future, such as the result of a network request. A stream, on the other hand, emits multiple values over time, like user input events or sensor data. Developers use stream listen to process these values as they arrive, enabling real-time data processing. For instance, a chat application might use a stream to receive messages as they are sent. Understanding the difference between futures and streams allows developers to choose the right tool for their specific use case, whether it's a one-time operation or continuous data flow. Dart's concurrency model offers a balance between simplicity and performance, making it suitable for a wide range of applications. The async await syntax simplifies asynchronous code isolates enable parallelism for CPU-heavy tasks. Streams and futures provide flexible ways to handle both single and multiple values over time. By mastering these concepts, developers can create efficient, scalable applications that handle I/O, user interactions, and background processes seamlessly. Whether building a simple mobile app or a complex web service, understanding Dart's concurrency model is essential for writing clean, high-performance code that meets modern demands. Streams in Dart are a powerful way to handle sequences of asynchronous data. Unlike traditional data structures that provide all their data at once, streams emit values over time, making them ideal for scenarios where data arrives incrementally. For instance, think of a live weather update or a chat application where new messages come in one after another. Streams allow your code to react to these events as they happen, rather than waiting for all data to be available upfront. This makes them essential for real-time applications, event-driven architectures, and any situation where you need to process data as it becomes available. Understanding streams is key to building responsive and efficient Dart applications. The Dart Stream API provides a robust framework for working with asynchronous sequences. At the core of this is the stream class, which represents a sequence of events that can be listened to over time. To create and manage streams, developers often use a stream controller. This controller acts as a bridge between the data source and the listeners, allowing you to manually add data to the stream. It's important to note that a stream itself is read-only, meaning you can only observe its events. The stream controller, on the other hand, is used to emit data into the stream. This separation of roles ensures that streams remain flexible and easy to manage. Whether you're building simple data pipelines or complex asynchronous workflows, creating streams in Dart is straightforward, with several methods available depending on your needs. The stream from iterable function is perfect for static data, such as a list of numbers or strings, where the entire dataset is known upfront. For recurring events, like a timer that fires every second, the stream periodic method is invaluable. It allows you to specify a duration and a callback that generates new values at regular intervals. Finally, when you need more control, you can use a stream controller to manually add data to the stream. This is particularly useful in scenarios where data is generated dynamically, such as reading from a sensor or handling user input in real time. Each method offers a different level of flexibility, so choosing the right one depends on your specific use case. Listening to streams is how you interact with the data they emit. The listen method is the primary way to receive stream events, allowing you to define a callback that processes each value as it arrives. But what happens if an error occurs during this process? That's where the on-error handler comes in. By providing an error callback, you can gracefully handle exceptions and prevent your application from crashing. Similarly, the on-done callback is triggered when the stream completes, signaling that no more data will be emitted. These three components, listen, on-error, and on-done, form the foundation of stream handling, ensuring your code can react to both successful and exceptional scenarios. Properly implementing these handlers is crucial for building reliable and user-friendly applications. Stream operators are tools that let you manipulate and transform stream data in powerful ways. The map operator allows you to apply a function to each event in the stream, transforming its values as they pass through. For example, you could convert a stream of numbers into a stream of strings. The where operator filters events based on a condition, so you only process data that meets specific criteria. Meanwhile, operators like take and skip give you control over how many events are processed. Take lets you limit the number of events, while skip lets you skip a certain number at the beginning. These operators can be chained together to create complex data pipelines, making it easy to clean, filter, and shape your stream data as needed. Error handling is a critical aspect of working with streams, as unexpected issues can arise at any time. The catch error method provides a way to catch and handle exceptions that occur within a stream, allowing your application to recover gracefully. Additionally, the on-error parameter in the listen method gives you detailed information about errors, such as the error object and stack trace. This information can be invaluable for debugging and logging. However, it's not enough to just handle errors. You should also implement strategies for recovery, such as retraying failed operations or notifying the user. By proactively addressing errors, you can ensure your application remains stable and resilient, even in the face of unpredictable data sources. Canceling streams is an important practice to prevent unnecessary resource consumption. When you no longer need a stream, you can call the cancel method on the subscription to stop listening. This is particularly important in long-running applications where failing to cancel streams can lead to memory leaks or performance issues. For example, if a stream is tied to a network request or a hardware sensor, not canceling it could keep the connection open indefinitely. Fortunately, streams are automatically canceled when the program ends, but it's still good practice to manage subscriptions manually. By canceling unused streams, you ensure your application remains efficient and avoids potential bugs caused by stale or unmanaged data. Understanding the difference between streams and futures is essential for choosing the right tool for the job. A future represents a single asynchronous value that will be available at some point in the future, like the result of a network request. In contrast, a stream represents a sequence of values that arrive over time, such as a series of sensor readings or chat messages. While futures are ideal for one-time operations, streams are better suited for continuous data flows. For example, if you're building an app that needs to monitor user activity or receive real-time updates, a stream would be the natural choice. Knowing when to use each construct allows you to design more efficient and maintainable code. Real-world applications often rely on streams to handle dynamic data. For instance, a real-time chat application might use a stream to receive and display new messages as they arrive. This allows users to see updates instantly without needing to refresh the page. Another example is a timer that triggers events at regular intervals, such as a countdown or a periodic data fetch. Streams are also useful for reading large files line by line, processing each line as it's read instead of loading the entire file into memory. These examples illustrate how streams can simplify complex asynchronous workflows, making it easier to build responsive and efficient applications. Following best practices when working with streams can greatly improve code quality and maintainability. One such practice is using the async syntax, which allows you to generate streams in a clean and readable way. This is especially useful for creating custom streams that emit data based on complex logic. Another key tip is to avoid blocking operations within stream handlers, as this can stall the entire application and lead to poor performance. testing streams with tools like Stream Tester helps ensure your code behaves as expected under various conditions. By adhering to these practices, you can write more reliable and scalable Dart applications that handle asynchronous data effectively. In conclusion, streams are a fundamental concept in Dart, enabling developers to handle asynchronous data with ease. By mastering their creation, manipulation, and error handling, you can build applications that are both responsive and robust. Remember to choose the right tools for your needs, whether it's a stream for continuous data or a future for single-value operations. As you practice with real-world scenarios, you'll gain the confidence and skills needed to leverage streams effectively in your projects. Keep exploring, experimenting, and refining your understanding. Streams are a powerful asset in any Dart developer's toolkit. Metaprogramming is a powerful concept in programming that allows developers to write code that can manipulate or generate other code. This means the code isn't just executing tasks, but can also create or modify parts of itself or other programs. This capability enables dynamic behavior, such as adapting to different scenarios at runtime, generating code on the fly to reduce repetition, and inspecting objects or types during execution. In Dart, metaprogramming is supported through several tools and features, including mirrors for runtime reflection, annotations to add custom metadata, and code generation tools like BuildRunner that create code during the compilation process. These tools make it easier to build flexible and maintainable applications. Dart provides three main features for metaprogramming: mirrors, annotations, and code generation. Mirrors are part of the Dart language and offer a reflective API that allows developers to inspect and modify objects, classes, and methods at runtime. This is useful for tasks like dynamically invoking methods or accessing properties. Annotations, on the other hand, are custom metadata that can be attached to classes, methods, or fields. They serve as markers or instructions for tools that process the code. Finally, code generation tools like BuildRunner are used to create additional code at compile time, which can automate repetitive tasks such as generating boilerplate code for serialization or dependency injection. These features work together to enhance the flexibility and efficiency of Dart development. One of the key tools for metaprogramming in Dart is the Mirrors Library, which is part of the Dart Mirrors package. This library includes classes like Mirror System, Class Mirror, and Method Mirror, which provide a way to inspect and interact with the structure of objects at runtime. For example, a developer can use Class Mirror to check the properties of a class, or Method Mirror to invoke a method dynamically. This is particularly useful in scenarios where the structure of the code isn't known in advance, such as in frameworks that need to adapt to different configurations. However, while mirrors offer powerful capabilities, they come with trade-offs, which we'll explore in the next slide. Despite their usefulness, mirrors in Dart have some significant limitations. One major drawback is the performance overhead they introduce. Since mirrors operate at runtime, they can slow down applications, especially in performance-critical environments. Additionally, mirrors are not supported in Flutter or Qt-compiled ahead-of-time compiled applications, which are common in mobile and web development. This makes them unsuitable for projects that require high performance or cross-platform compatibility. As a result, the Dart community has largely moved away from using mirrors for most tasks, favoring alternative approaches like code generation that offer better performance and broader compatibility. Annotations are another essential tool for metaprogramming in Dart. These are custom metadata elements that can be attached to classes, methods, or fields to provide additional information. For example, an annotation might indicate that a class should be serialized, or that a method requires dependency injection. Annotations themselves don't perform any actions, but serve as instructions for code generators. Tools like BuildRunner process these annotations to generate additional code automatically. This approach is widely used in scenarios such as JSON serialization, where annotations guide the generation of methods like from JSON and to JSON, eliminating the need for manual boilerplate code. To illustrate how annotations work, let's consider an example. Suppose we define an annotation called @JSON serializable. This annotation can be applied to a class to indicate that it should be serialized. A code generator, such as the JSON serializable package, then reads this annotation and generates the necessary methods, such as from JSON and to JSON, to convert the class's data to and from JSON format. This process happens at compile time, ensuring that the generated code is efficient and free of runtime overhead. By using annotations, developers can focus on writing clean, readable code while letting tools handle the repetitive tasks, leading to more maintainable and scalable applications. The benefits of metaprogramming in Dart are numerous. One of the most significant advantages is the reduction of boilerplate code. Instead of writing repetitive code manually, developers can use annotations and code generation tools to automate these tasks. This not only saves time, but also reduces the likelihood of errors. Metaprogramming also improves maintainability, as changes to the code base can be centralized in annotations or generators rather than spread across multiple files. Additionally, it enables the creation of dynamic frameworks and plugins that can adapt to different use cases, making Dart a versatile choice for a wide range of applications. While metaprogramming offers many advantages, it's important to use it judiciously. Overusing features like mirrors or annotations can lead to complex, hard-to-maintain code. Developers should prioritize clarity and performance, avoiding unnecessary complexity. Where possible, it's better to rely on code generation instead of runtime reflection, as the former is more efficient and compatible with a wider range of environments. Additionally, documenting metaprogramming logic is crucial, as it helps team members understand how annotations, generators, or reflective code work. By following these best practices, developers can harness the power of metaprogramming without compromising the quality or performance of their applications. In conclusion, Dart's metaprogramming tools provide a powerful way to enhance flexibility and productivity in software development. While mirrors offer runtime reflection, they come with limitations that make them less suitable for modern applications. Instead, code generation via annotations has become the preferred approach, offering better performance, compatibility, and maintainability. By leveraging these tools effectively, developers can write cleaner, more efficient code that adapts to evolving requirements. As the Dart ecosystem continues to grow, metaprogramming will remain a valuable technique for building robust and scalable applications. Dart's type system is a foundational element that ensures code reliability and reduces runtime errors. It acts as a safety net, guiding developers to write predictable and maintainable code. When building complex applications, understanding advanced type features becomes essential. These features allow for more robust code structures, enabling developers to handle edge cases, improve code clarity, and enforce stricter constraints. The key areas we will explore today include null safety, which prevents null-related crashes, generics, which enable reusable and type-safe code, type promotion, which allows for smarter type handling, and type inference, which simplifies code by letting the compiler deduce types automatically. Together, these tools empower developers to write safer, more efficient, and scalable Dart applications. Null safety is a cornerstone of modern Dart development. By making types non-nullable by default, Dart eliminates the possibility of null references, causing runtime errors. This approach forces developers to explicitly handle cases where a value might be absent. For example, declaring a variable as string name equals Dart ensures it will never be null, while string name equals null allows for the possibility of absence. To manage null values safely, Dart provides null-aware operators. The question mark allows for optional chaining. The exclamation mark asserts non-null. The double question mark provides a fallback value, and the question dot operator performs a null-aware assignment. Additionally, the late keyword allows for delayed initialization, ensuring a variable is assigned before use. These features collectively create a robust framework for handling null values without sacrificing code clarity or safety. Generics are a powerful tool for creating flexible and reusable code. By using type parameters like T, developers can design classes, methods, and functions that work with any data type while maintaining type safety. For instance, a list of integers list, int, ensures all elements are integers, whereas a list of dynamic types list dynamic allows for any object, which can lead to runtime errors. Generic methods, such as tFindFirst, tList, enable operations that adapt to the data type they are working with. This not only reduces the need for explicit typecasting, but also ensures that errors are caught at compile time rather than runtime. By leveraging generics, developers can write more concise and maintainable code that is less prone to type-related issues. Type promotion and casting are critical for handling dynamic data safely. When a variable is checked against a specific type, such as string, Dart automatically promotes its type within the scope of that check, allowing for direct access without explicit casting. For example, if obj is string, string S equals obj ensures that S is treated as a string. However, when the type is not known at runtime, explicit casting, using the as operator becomes necessary. While this provides flexibility, it must be used cautiously to avoid runtime errors. Combining the is and as operators allows for safe type checks and conversions, ensuring that the code remains robust even when dealing with unknown or variable types. This balance between automatic promotion and manual casting gives developers the tools to handle complex type scenarios effectively. Type inference in Dart simplifies code by allowing the compiler to deduce types based on context. Using var and final, developers can declare variables without explicitly stating their types, relying on the compiler to infer them. For example, var list equals 1, 2, 3 infers the type as list int, making the code cleaner and more readable. However, this convenience comes with limitations. Overusing dynamic types can undermine the benefits of type inference, leading to potential runtime errors. It is best practice to prefer explicit types for clarity and safety, especially in larger code bases. Understanding when to use inference and when to specify types ensures that code remains both efficient and maintainable. Striking a balance between simplicity and precision. Type aliases created with the typedef keyword allow developers to define custom names for complex types, improving code readability and maintainability. For example, typedef void func equals void function simplifies the declaration of functions that return no value. Similarly, typedef map result equals map string list int creates a shorthand for a nested data structure, making the code easier to understand. These aliases are particularly useful when working with intricate type hierarchies or callback functions, as they reduce repetition and make the code more expressive. By using type aliases, developers can write cleaner, more organized code that is easier to debug and maintain, especially in large-scale applications. Extension methods provide a way to add functionality to existing types without modifying their source code or using inheritance. This feature allows developers to enhance the behavior of classes, interfaces, or even built-in types. For example, an extension on listInt can define a sum method that calculates the total of all elements, enabling syntax syntax like 1, 2, 3 sum to return 6. This approach promotes code reusability and clarity, as it keeps the original type's definition intact while extending its capabilities. Extension methods are particularly useful for adding utility functions that are specific to a type, making the code more intuitive and reducing the need for helper functions. By leveraging this feature, developers can write more expressive and efficient code that is easier to read and maintain. Mastering advanced type features in Dart is essential for writing safe, scalable, and maintainable code. Null safety ensures that developers handle null values explicitly, reducing runtime crashes. Generics enable reusable and type-safe code, while type promotion and casting allow for flexible yet controlled type handling. Type inference simplifies code by letting the compiler deduce types, but it should be used judiciously. Type aliases and extension methods further enhance code readability and reusability, making complex structures more manageable. By prioritizing explicit types over dynamic and applying these features in real-world scenarios, developers can build robust applications that are easier to debug, test, and scale. Practicing these concepts regularly will solidify your understanding and improve your ability to leverage Dart's powerful type system effectively. Dart is a versatile language for web development, supporting both client-side and server-side applications. This means you can use Dart to build interactive user interfaces in the browser, as well as manage backend operations. Dart's strong typing ensures that errors are caught early during development, which leads to more reliable and scalable web apps. Additionally, Dart can compile to JavaScript, allowing your code to run seamlessly across different platforms. This compilation process translates Dart code into optimized JavaScript, making it compatible with any modern web browser. Whether you're building a simple static site or a complex single-page application, Dart provides the tools to handle it efficiently. To set up your development environment, start by installing the Dart SDK, which includes the core libraries and tools needed for Dart development. If you're targeting web applications, you'll also need to install Flutter, as it provides the necessary frameworks and tools for building web projects. Once the SDK is installed, choose an IDE like Visual Studio Code or Android Studio, both of which have robust Dart plugins for code highlighting, debugging, and project management. To initialize a new project, use the command flutter create platforms web, which generates a project structure optimized for web development. This setup ensures you have all the necessary dependencies and configurations to start coding immediately. Dart's Dart HTML library is essential for manipulating the document object model in web applications. This library provides classes and methods to interact with HTML elements, such as changing content, styling, or handling user input. Event handling is another critical aspect, allowing your app to respond to user actions like clicks, form submissions, or keyboard inputs. For example, you can attach event listeners to buttons to trigger specific functions. Asynchronous programming in Dart uses futures and a sync await to manage tasks that take time, such as fetching data from a server. This approach keeps your app responsive and avoids blocking the main thread, which is crucial for delivering a smooth user experience. Dart can directly interact with HTML elements using methods like query selector, which allows you to access and modify specific parts of the DOM. For instance, you can retrieve a button element and update its text dynamically. Styling web apps can be done through traditional CSS files, which are easier to manage for large projects. Alternatively, Dart's Dart UI library enables dynamic styling by creating and modifying styles programmatically. When integrating with JavaScript, Dart's Dart.js library provides a bridge to call existing JavaScript code or use third-party libraries. This interop capability is useful for leveraging legacy systems or libraries that aren't available in Dart, ensuring flexibility in your development workflow. Building a simple web app starts with creating a basic HTML structure, which is often handled by the main Dart file in a Flutter web project. For example, a counter app might have a button and a text element that updates when the button is clicked. To add interactivity, you'll attach event listeners to the button, which trigger a function to increment a counter variable. This function then updates the DOM to reflect the new value. By combining Dart's event handling and DOM manipulation, you can create dynamic and responsive user interfaces. This example demonstrates how Dart simplifies the process of building interactive web components without relying heavily on raw JavaScript when optimizing Dart web applications. It's important to minimize JavaScript interop, as frequent calls between Dart and JavaScript can introduce performance overhead. Instead, leverage Dart's built-in libraries, which are optimized for efficiency, and reduce the need for external dependencies. For instance, using Dart's native HTTP library for API calls is faster than relying on JavaScript equivalents. Additionally, Flutter for Web ensures a consistent UI across platforms by abstracting platform-specific details. This means you can build a single code base that works seamlessly on desktop, mobile, and web, saving time and effort while maintaining a high level of performance. For complex apps, state management is crucial. Dart developers often use Provider or Riverpod to manage and share data across different parts of the application. These tools help maintain a clean architecture by separating the UI logic from the data layer. Routing in Dart web apps can be handled with Flutter Router, which allows you to navigate between different screens or views based on user interactions. Integrating web APIs, such as fetching data from a REST-TFL service, involves making asynchronous requests and updating the UI accordingly. By combining these advanced techniques, you can build scalable and maintainable web applications that handle complex interactions and data flows. Best practices for Dart web projects include organizing code into modular packages to improve readability and reusability. This approach allows you to break down large projects into smaller, manageable components. Version control systems like Git are essential for collaboration, enabling multiple developers to work on the same project without conflicts. Testing is another key aspect. Using Dart Test and Flutter Test ensures that your code functions as expected and reduces the risk of bugs. By following these practices, you create a more structured and reliable development process, making it easier to scale and maintain your web applications over time. Dart offers powerful tools for web development with strong typing and performance, making it an excellent choice for building modern web applications. By combining Dart's features with HTML, CSS, and JavaScript, you can create full-stack solutions that are both efficient and scalable. Whether you're working on a small project or a large enterprise application, mastering Dart's web capabilities requires hands-on practice. Building real-world projects helps reinforce your understanding and allows you to explore advanced techniques, ultimately unlocking the full potential of Dart in web development. Firebase is a backend-as-a-service platform that simplifies app development by providing a suite of tools and services to handle server-side logic, databases, authentication, and more. This allows developers to focus on building the user-facing parts of their applications without worrying about the complexities of managing servers or infrastructure. Dart, on the other hand, is a programming language designed specifically for building cross-platform applications, whether for mobile, web, or desktop. When integrated with Firebase, Dart apps gain the ability to sync data in real time, manage user authentication seamlessly, and store files in the cloud. This combination empowers developers to create rich, feature-packed applications with minimal backend code, accelerating the development process and reducing the need for custom server solutions. Before integrating Firebase with a Dart project, there are several prerequisites to address. First, you need to install the Dart and Flutter SDKs, which provide the necessary tools and frameworks for app development. Next, create a Firebase project in the Firebase console, where you can configure and manage all Firebase services. Once the project is set up, you must add Firebase to your Dart or Flutter app by including the Firebase core package in your dependencies. This step ensures that your app can communicate with Firebase services. Finally, configure the specific Firebase services you plan to use, such as authentication, Firestore, or cloud storage. By setting up the necessary rules and permissions in the Firebase console, these steps lay the foundation for a secure and functional integration. To begin using Firebase in a Dart application, the first step is to initialize Firebase in your app's main file, typically main Dart, using the Firebase initialize app method. This initializes the Firebase SDK and prepares it for use. Next, you must add the required Firebase dependencies to your PubSpec YAML file, such as Firebase Auth for authentication or Cloudflare Store for database access. It's also crucial to use environment variables to store sensitive Firebase configuration details, such as API keys or project IDs, to avoid hard-coding them into your app. Additionally, you should implement error handling to manage any issues that may arise during the initialization process, ensuring your app remains robust and user-friendly even if Firebase fails to load. Firebase offers a range of services that are particularly useful for Dart applications. The authentication service allows users to sign in using email, phone numbers, or third-party providers like Google or Facebook, making it easy to manage user identities. Firestore is a NoSQL cloud database that enables real-time data synchronization, allowing your app to respond instantly to changes in data. The real-time database, another option, stores data in a hierarchical structure and provides real-time updates, making it ideal for applications like chat apps or collaborative tools. Cloud storage is designed for storing files such as images or videos, while cloud messaging allows you to send push notifications to users. Together, these services provide a comprehensive backend solution that enhances the functionality of Dart apps. Firebase authentication in Dart is managed through the Firebase Auth class, which provides methods for user sign-in, registration, and session management. You can implement various sign-in methods, such as email and password, phone authentication, or social logins using OAuth providers. To monitor user authentication state, the auth state changes method is particularly useful, as it allows your app to respond to changes like a user logging in or out. By leveraging these features, you can secure different parts of your app based on user roles, ensuring that only authorized users can access specific features or data. This level of control is essential for maintaining the security and integrity of your application. Integrating Firestore with Dart involves connecting to the Firestore instance and performing CRUD operations to manage data. For example, you can use the add method to insert new documents into a collection, get to retrieve data, update to modify existing data, and delete to remove it. To enable real-time updates, the Stream Builder widget is commonly used, which listens for changes in the database and automatically updates the UI. As an example, you might fetch user data from a Firestore collection by querying the database and displaying the results in a list. This approach ensures that your app remains responsive and up to date with the latest information. The real-time database in Firebase is designed for storing data in a JSON-like structure, making it easy to work with hierarchical data. To listen for real-time updates, you can use the on-value listener, which triggers whenever the data at a specific location changes. This is particularly useful for applications like chat apps, where new messages need to be displayed instantly. Compared to Firestore, the real-time database is more suited for scenarios where data is structured in a tree-like format, while Firestore is better for document-based, flexible data models. Understanding the differences between these two services helps you choose the right tool for your specific use case. Cloud storage in Firebase allows Dart applications to upload and retrieve files such as images, videos, or documents. To upload a file, you can use the put file method, which takes a local file and uploads it to a specified location in Firebase storage. To download a file, you can retrieve its download URL using Get Download URL, which enables your app to access the file later. Managing storage rules in the Firebase console is also critical, as these rules determine who can read or write to your storage. For instance, you might use cloud storage to store user profile images, ensuring that only authenticated users can upload or view their own images. Implementing cloud messaging in Dart requires integrating the Firebase messaging package, which enables your app to receive push notifications. The first step is to request permission from the user to send notifications, which is done using the request permission method. Once permission is granted, you can handle messages in both the foreground and background by setting up listeners for incoming notifications. For example, you might send a notification to a specific user by targeting their unique device token. This feature is invaluable for engaging users and keeping them informed about important updates or events within your app. When integrating Firebase with Dart, following best practices is essential for security and performance. One of the most critical steps is securing Firebase rules, such as ensuring that only authenticated users can access certain data. Using try-catch blocks for error handling helps manage exceptions gracefully, improving the user experience. Optimizing queries by limiting the amount of data retrieved or using indexes can prevent performance issues, especially in large datasets. Additionally, leveraging Firebase UI components can save development time by providing pre-built authentication widgets that handle common use cases. These practices ensure that your app is both secure and efficient. Integrating Firebase with Dart can present challenges that require careful troubleshooting. For example, authentication errors often stem from misconfigured Firebase settings, so checking the Firebase console for any issues is a good first step. Data sync issues can be resolved by using Stream Builder to ensure real-time updates are properly handled. Security rules may need adjustments, and testing them in the Firebase console can help identify and fix any vulnerabilities. Performance problems, such as slow queries, can be mitigated by using pagination or adding indexes to your Firestore collections. Addressing these challenges proactively ensures a smoother development process and a more reliable app. In summary, integrating Firebase with Dart unlocks a powerful set of tools for building modern, feature-rich applications. The key services authentication, Firestore, cloud storage, and cloud messaging provide the backbone for real-time data, user management, and communication. By adhering to best practices for security and scalability, developers can create applications that are both robust and user-friendly. The best way to master these concepts is to practice by building a sample app that incorporates real-time features, allowing you to apply what you've learned in a practical context. This hands-on approach reinforces your understanding and prepares you for real-world development scenarios. Testing is a critical component of developing reliable and high-quality Dart applications. When we write tests, we ensure that our code behaves as expected under various conditions, which directly contributes to its reliability and correctness. Dart provides a robust set of built-in tools that allow developers to perform unit tests, widget tests, and integration tests. These tools help verify that individual functions, user interface components, and entire app workflows operate properly. By investing time in testing, we not only catch bugs early, but also make our code base easier to maintain over time. Testing acts as a safety net, allowing us to make changes with confidence and reducing the likelihood of introducing new issues. Dart supports 3 primary types of tests, each serving a unique purpose. Unit tests focus on testing individual functions or methods in isolation, ensuring that each part of the code works correctly on its own. Widget tests are specific to Flutter and are used to validate the behavior of user interface components, such as buttons, text fields, and custom widgets. These tests help confirm that the UI renders and responds to user interactions as intended. Integration tests, on the other hand, simulate real user scenarios and test the interaction between different parts of the application. These tests are essential for verifying that the app functions as a whole, from the user interface down to the underlying logic. Understanding the distinction between these test types allows developers to choose the right approach for each part of their application. To implement testing in Dart, developers rely on several key packages. The test package is the core testing framework, providing the foundational tools for writing and running tests. It offers functions like test and setup to structure and organize test cases. The Mockito package is used to create mock objects, which replace real dependencies during testing. This allows developers to isolate the code under test and avoid external factors that might affect the results. For Flutter-specific testing, the FlutterDist package provides utilities tailored to the framework, such as methods for interacting with widgets and simulating user actions. Together, these packages form a comprehensive ecosystem that empowers developers to write thorough and effective tests. Writing unit tests in Dart is straightforward and follows a clear structure. The test function is used to define individual test cases, and the expect function checks whether the actual result matches the expected outcome. For example, a simple test might verify that adding 2 and 2 equals 4. In addition to the test function, developers can use setup and teardown to prepare and clean up the testing environment before and after each test. This ensures that tests are independent and do not interfere with one another. By organizing tests into logical groups and using these setup functions, developers can create a maintainable and efficient testing suite that covers all critical parts of their code. Widget testing in Flutter requires a slightly different approach, as it involves rendering and interacting with the user interface. The tester pump widget method is used to build and display a widget in the testing environment, allowing developers to inspect its properties and behavior. For instance, a test might check that a counter widget initially displays the value 0. By simulating user interactions, such as taps or scrolls, developers can verify that the widget updates its state correctly. Widget tests are essential for ensuring that the UI components behave as expected and that the user experience remains consistent across different scenarios. These tests provide confidence that the visual elements of the app function properly under real-world conditions. Integration tests are designed to validate the entire application workflow, simulating how users interact with the app from start to finish. The integration test package provides the tools needed to write these tests, allowing developers to perform actions like tapping buttons, entering text, and navigating between screens. Unlike unit tests, integration tests do not rely on mocking dependencies, which means they test the app in a more realistic environment. This approach helps uncover issues that might not be apparent during unit testing, such as problems with data flow or unexpected interactions between components. By testing the app as a whole, integration tests ensure that all parts work together seamlessly, providing a comprehensive check of the application's functionality. To create effective tests, developers should follow several best practices. First, it is important to write tests for edge cases and error scenarios, as these often reveal hidden bugs. For example, a test might check how the app handles invalid input or network failures. Keeping tests isolated and fast is also crucial, as this ensures that tests can be run frequently without causing delays. Using mocking techniques allows developers to replace external dependencies, such as APIs or databases, with simulated versions, making tests more reliable and easier to maintain. Finally, maintaining high test coverage for critical code paths ensures that the most important parts of the application are thoroughly tested, reducing the risk of critical failures in production. Measuring test coverage is an essential part of the testing process, as it helps identify areas of the code that may not be adequately tested. Dart provides a built-in command, Dart test coverage, which generates a detailed report on which parts of the code are covered by tests. This report highlights lines of code that are not executed during testing, allowing developers to focus on improving coverage where it is most needed. Integrating test coverage analysis into continuous integration and delivery pipelines ensures that tests are run automatically and that new code changes do not introduce untested functionality. By leveraging these tools, teams can maintain a high standard of code quality and ensure that their applications remain robust and reliable. Testing in Dart often follows established patterns that improve clarity and maintainability. The arrange, act, assert AAA pattern is a common approach where tests are structured into 3 distinct phases: arranging the necessary conditions, acting by invoking the code under test, and asserting that the expected outcome is achieved. This structure makes tests easier to read and understand. Mocking is another essential technique where real dependencies are replaced with mock objects to isolate the code being tested. This allows developers to focus on the logic without worrying about external factors. Parameterized tests, which run the same test with multiple input values, are also useful for verifying that code handles a variety of scenarios correctly. These patterns help create a more efficient and effective testing process. In conclusion, testing is a fundamental practice for building reliable and maintainable Dart applications. By leveraging the built-in tools and packages available in the Dart ecosystem, developers can write comprehensive tests that cover all aspects of their code. Whether through unit tests, widget tests, or integration tests, each approach plays a vital role in ensuring the quality of the application. Prioritizing test quality and maintainability not only improves the development process, but also leads to a more stable and user-friendly product. As the complexity of applications grows, a strong testing strategy becomes even more critical, helping teams deliver high-quality software with confidence. Debugging is the process of identifying and fixing errors in code. It is a fundamental skill for any developer, as it ensures that applications behave as intended and perform efficiently. When code contains bugs, it can lead to unexpected behavior, crashes, or even security vulnerabilities. In Dart, debugging is not just about fixing syntax errors, but also about understanding the flow of data and logic within an application. Tools like dev tools, print statements, and breakpoints are essential for this process. By mastering these techniques, developers can build more reliable and robust applications, ultimately saving time and improving user experience. Dart Dev Tools is a comprehensive suite of performance and debugging tools designed to help developers analyze and optimize their Dart and Flutter applications. It provides insights into various aspects of an application's behavior, such as CPU usage, memory allocation, and network activity. This allows developers to pinpoint performance bottlenecks and resolve them effectively. One of the key features of DevTools is its ability to debug the Dart virtual machine, enabling developers to inspect variables, trace execution paths, and examine stack traces. Accessing DevTools is straightforward, either through the command line using the Dart DevTools command, or through integrated support in popular IDEs like Visual Studio Code and Android Studio. This flexibility makes it an indispensable tool for both beginners and experienced developers. Print statements are one of the simplest and most widely used debugging techniques. By using the print function, developers can output variable values, log execution flow, or track the state of an application at specific points. For example, print_value of x can help identify unexpected values during runtime. However, print statements have limitations, especially when dealing with complex data structures like nested objects or large lists. In such cases, the output can become overwhelming or difficult to interpret. To address this, Dart provides the debug print function, which is particularly useful in Flutter applications. It offers better formatting and handles larger data structures more effectively, making it a preferred choice for debugging in UI-heavy projects. Setting breakpoints in an integrated development environment is a powerful way to pause execution and inspect the state of an application. Popular IDEs like Visual Studio Code and Android Studio allow developers to set breakpoints by clicking on the gutter next to the code. Once a breakpoint is hit, the application pauses, enabling developers to step through code line by line. Tools like Step Over, Step Into, and Step Out allow for precise control over execution flow. For instance, Step Over executes the current line and moves to the next, while Step Into dives into a function call. During pauses, developers can inspect variables, evaluate expressions, and even modify values to test different scenarios. However, it is important to note that breakpoints only work when the application is running in debug mode, which is typically enabled through the IDE or command line. Debugging in Dart often involves addressing common issues that arise during development. Null reference errors are a frequent problem, especially in applications that rely on null safety. Checking for null values and using optional types can help prevent these errors. Async await issues, such as unhandled exceptions or incorrect sequencing of asynchronous operations, can be tackled using try-catch blocks and debugging futures. For UI rendering problems, Dart DevTools provides a widget tree inspector, allowing developers to visualize and debug the structure of their user interface. Performance bottlenecks, such as excessive CPU usage or memory leaks, can be identified and resolved using the profiling tools within DevTools. By understanding these scenarios and leveraging the right tools, developers can efficiently troubleshoot and optimize their applications. Effective debugging requires a systematic approach and adherence to best practices. One of the first steps is to reproduce the issue consistently, as this ensures that the problem can be tested and verified. Version control systems like Git can help isolate recent changes that might have introduced the error. Writing unit tests is another critical practice, as it allows developers to catch regressions and validate fixes. Documenting debugging steps and findings is equally important, as it helps avoid repeating the same mistakes and provides a reference for future issues. By combining these practices with the tools available in Dart, developers can create a more efficient and reliable debugging workflow. Debugging is a critical skill for any Dart developer, as it directly impacts the quality and performance of applications. By leveraging tools like DevTools, print statements, and breakpoints, developers can systematically identify and resolve issues. However, debugging is not just about using the right tools. It also requires patience, attention to detail, and a structured problem-solving approach. Practicing these techniques regularly and staying updated with new features in Dart and Flutter will enhance a developer's ability to tackle complex challenges. Ultimately, continuous learning and experimentation are key to becoming proficient in debugging and ensuring the success of any Dart project. Flutter is a powerful UI toolkit designed to help developers create natively compiled applications for mobile, web, and desktop platforms. Unlike traditional frameworks that rely on platform-specific code, Flutter allows you to write a single code base that works across multiple operating systems. At the heart of Flutter is the Dart programming language, which offers a modern, object-oriented syntax with strong typing and performance optimizations. Dart's design makes it particularly well-suited for building dynamic and responsive user interfaces. When combined with Flutter's reactive, declarative approach, developers can construct rich, visually appealing applications using a vast library of pre-built widgets. This synergy between Dart and Flutter ensures that developers can focus on creating intuitive experiences without compromising on speed or functionality. One of the standout features of Flutter is its ability to support cross-platform development, meaning you can build apps for iOS, Android, web, and desktop with a single code base. This not only saves time, but also ensures consistency in design and behavior across devices. Another key advantage is Hot Reload, a feature that allows developers to see changes in the app instantly without restarting the application. This significantly speeds up the development process and encourages rapid iteration. Flutter's single code base approach reduces the complexity of maintaining separate code bases for different platforms, making it easier to scale and update applications. Additionally, Flutter's rendering engine, Skia, ensures high-performance graphics and animations, even on lower-end devices. The framework also includes a comprehensive set of built-in widgets, such as material design components and Cupertino widgets for iOS-style interfaces, which simplifies the creation of visually cohesive applications. When it comes to mobile development, Dart provides robust tools for handling asynchronous operations, such as network requests and I/O tasks, through its async await syntax. This makes it easier to write clean and maintainable code for tasks like fetching data from APIs or interacting with local storage. Dart's null safety feature is a game changer, as it helps prevent runtime errors by ensuring variables are either explicitly nullable or non-nullable. This leads to more reliable and stable applications. The Dart ecosystem, hosted on PubDev, offers a wealth of third-party libraries that can be integrated into Flutter projects, expanding functionality without reinventing the wheel. Developers can also seamlessly connect Flutter apps to services like Firebase for real-time data, REST APIs for back-end communication, and local databases for offline functionality. Furthermore, Dart's compatibility with Flutter's widget system allows for the creation of dynamic, interactive UIs that respond to user input and data changes in real time. Understanding the structure of a Flutter project is essential for efficient development. The lib directory is where the core logic and UI components of the app are written, including all Dart files. The pubspec YAML file acts as the project's manifest, defining dependencies, assets, and metadata such as the app's name and version. Assets like images, fonts, and other static files are stored in the Assets folder, which can be accessed throughout the app. The main Dart file serves as the entry point, where the app's root widget is initialized. For platform-specific configurations, Flutter provides separate folders like Android and iOS, which contain settings and code tailored to each operating system. This structure ensures that developers can organize their code effectively while maintaining flexibility for platform-specific customizations. In Flutter, everything is built using widgets, which are the fundamental building blocks of the UI. Widgets can range from simple elements like container, text, and row to more complex components like list view and grid view. Stateless widgets are used for static UIs that do not change after being created, making them ideal for displays like labels or icons. On the other hand, stateful widgets, which extend stateful widget, allow for dynamic UIs that can update in response to user interactions or data changes. Layout widgets such as padding, margin, and expanded help structure the UI for different screen sizes and orientations, ensuring a responsive design. By creating custom widgets, developers can encapsulate reusable UI components, promoting code reuse and maintaining a consistent design language across the application. Managing state is a critical aspect of any Flutter app, and there are multiple approaches to achieve this. The simplest method involves using setState within a stateful widget, which triggers a rebuild of the widget when the state changes. For more complex applications, advanced state management solutions like Provider, Riverpod, Block, or GetX offer scalable and organized ways to handle data flow. Understanding the widget lifecycle is also essential, as methods like initState and dispose allow developers to initialize and clean up resources at the right times. Effective state management ensures that data is consistently updated across different parts of the app, whether it's a single screen or multiple interconnected widgets. By choosing the right strategy, developers can create applications that are both maintainable and efficient. Networking and API integration are vital for modern mobile applications, and Dart provides several tools to simplify this process. The HTTP package, or its alternative, DO, allows developers to make REST API calls, fetch data from servers, and send requests with ease. Parsing JSON data is streamlined using Dart's built-in Dart convert library or third-party packages like JSON serializable for automatic serialization. Asynchronous programming with future and stream enables developers to handle data loading, updates, and user interactions without blocking the UI. Proper error handling and loading states ensure a smooth user experience, even when network conditions are unpredictable. By integrating with backend services or third-party APIs, Flutter apps can access real-time data, authenticate users, and perform a wide range of functionalities, making them more interactive and powerful. Optimizing performance is crucial for delivering a smooth and responsive user experience. One technique is to use const constructors for widgets that do not change, which reduces memory usage and improves rendering speed. Avoiding unnecessary widget rebuilds can be achieved by using key objects or value listenable to control when parts of the UI update. Flutter Dev Tools provides a suite of profiling tools to analyze CPU, memory, and network usage, helping identify and fix performance bottlenecks. Image loading can be optimized using Image Network, along with caching strategies to minimize data usage and loading times. Finally, techniques like tree shaking remove unused code from the final app, reducing its size, while asset optimization ensures that images and other resources are compressed without sacrificing quality. These practices collectively contribute to a faster, more efficient application. In conclusion, Dart and Flutter offer a powerful and efficient framework for mobile development, combining the strengths of a modern programming language with a flexible UI toolkit. Mastering Dart's syntax and Flutter's widget system is essential for building high-quality, scalable applications. Focusing on state management, UI design, and performance optimization ensures that apps can handle complexity while delivering a seamless user experience. By leveraging Dart's extensive ecosystem and Flutter's cross-platform capabilities, developers can streamline their workflow and reduce time to market. The best way to solidify these skills is by building real-world applications, experimenting with different features, and continuously refining your approach. With dedication and practice, you can unlock the full potential of Dart and Flutter to create innovative and impactful mobile solutions. State management is a critical concept in application development, particularly in Dart and Flutter. It involves the process of handling and updating application data in a way that ensures the user interface stays in sync with the underlying data. This is essential because, without proper state management, the UI may not reflect changes in the data, leading to a poor user experience. For instance, if a user updates their profile information, the app must dynamically update all relevant parts of the interface to show the new data. Poorly implemented state management can result in a variety of issues, including unexpected bugs, sluggish performance due to inefficient updates, and difficulty in maintaining and scaling the application over time. Therefore, understanding and implementing effective state management strategies is a foundational skill for any Dart or Flutter developer. When it comes to state management in Dart and Flutter, there are several techniques available, each suited to different scenarios. The most basic approach is the stateful widget, which is ideal for small applications where the state is simple and localized. For more structured projects, the provider package offers a lightweight and easy-to-integrate solution that allows for centralized data storage and efficient updates. Riverpod builds upon provider, enhancing scalability and testability while addressing some of its limitations. The below-C pattern takes a more advanced approach by separating the business logic from the UI, making the application more modular and easier to test. Finally, the GetX framework provides a comprehensive solution that combines state management, routing, and dependency injection, making it a popular choice for rapid development. Each of these techniques has its strengths and trade-offs, and the choice depends on the specific needs of the project. Provider is a widely used state management solution in the Flutter ecosystem. It leverages the change notifier class to notify widgets of state changes, ensuring that the UI updates automatically. The consumer widget allows for efficient access to the state without requiring the entire widget tree to rebuild, which optimizes performance. One of the key benefits of Provider is its simplicity, making it an excellent choice for developers who are new to state management or working on smaller projects. It integrates seamlessly with Flutter's widget tree, allowing for a clean and organized code structure. However, as applications grow in complexity, Provider may struggle to handle intricate state flows, making it less less suitable for large-scale projects that require more robust solutions. RiverPod is a modern evolution of provider that addresses many of its limitations, making it a preferred choice for medium to large applications. Built on the same principles as provider, RiverPod introduces improved dependency management and better support for asynchronous operations. One of its standout features is the ability to avoid relying on the build context, which can lead to more stable and predictable state updates. This makes it easier to test and maintain the application, especially in complex scenarios. RiverPod also simplifies the process of managing dependencies, reducing the risk of errors that can occur with traditional provider implementations. Its design encourages scalability, allowing developers to build applications that can grow without compromising performance or maintainability. The below-C pattern is a powerful approach to state management that separates the user interface logic from the business logic of the application. By using streams and sinks, below-C enables the application to handle state changes in a reactive and event-driven manner. This separation makes the code base more modular, easier to test, and less prone to errors. For example, when a user interacts with the app, the event is processed by the below-C, which then emits a new state that the UI can react to. This decoupling of concerns not only improves maintainability, but also allows for greater flexibility in handling complex workflows. However, mastering below-C requires a solid understanding of streams and reactive programming concepts, which may present a learning curve for some developers. The GetX framework offers a unique combination of state management, routing, and dependency injection in a single, lightweight package. This makes it an attractive option for developers looking to streamline their workflow and reduce the need for multiple libraries. GetX utilizes methods like getPut to register stateful objects and getBuilder to listen for changes and update the UI accordingly. Its simplicity and speed make it particularly well suited for rapid development and smaller projects. However, while GetX is efficient for basic use cases, it may not provide the same level of advanced features or flexibility as more specialized solutions like below-C or RiverPod. Developers should evaluate their project requirements to determine whether GetX's simplicity aligns with their long-term goals. Choosing the right state management approach depends on the size and complexity of the application, as well as the team's expertise. For small applications with limited state requirements, a stateful widget or provider can be sufficient, offering a straightforward and quick implementation. For medium-sized projects, RiverPod or Below C provides a balance between simplicity and scalability, allowing the application to grow without sacrificing performance. In larger projects, where maintainability and testability are critical, Below C or RiverPod are often the preferred choices due to their robust architecture. Additionally, the team's familiarity with the chosen framework can influence the decision, as adopting a tool that the developers are comfortable with can significantly impact the project's success. Adhering to best practices in state management can greatly enhance the quality and maintainability of a Flutter application. One key principle is to keep the state immutable, which helps prevent unexpected side effects and makes the code easier to reason about. RiverPod is particularly well suited for this approach, as it encourages a clean and predictable state management flow. Avoiding the overuse of stateful widget for complex state scenarios can also prevent performance issues and make the code base more manageable. When dealing with asynchronous operations, leveraging streams or futures ensures that the application can handle data loading and updates efficiently. By following these practices, developers can create applications that are not only functional, but also scalable and easy to maintain over time. Effective state management is the cornerstone of a well-designed Flutter application. It ensures that the app behaves predictably, responds to user interactions smoothly, and remains adaptable to future changes. The choice of state management tools should be guided by the specific needs of the project, including its size, complexity, and the team's level of expertise. Whether using a simple stateful widget or a more advanced framework like Below C or RiverPod, the goal is to create a code base that is both efficient and maintainable. By mastering these concepts, developers can significantly improve the performance, reliability, and longevity of their Flutter applications, ultimately delivering a better experience for end users. Generics in Dart are a powerful feature that allows developers to create flexible and reusable code by parameterizing types. This means that classes, interfaces, and functions can operate on types that are specified at the time of their creation. For example, Instead of writing separate code for a list of strings, a list of integers, or a list of custom objects, you can define a single generic class like box T that works with any type. This approach not only reduces code duplication, but also ensures that your collections are type safe. By using generics, you avoid the need for manual typecasting, which can lead to runtime errors. A common example is the list string type, which guarantees that the list will only contain string values, preventing accidental insertion of other types. This makes your code more robust and easier to maintain. The benefits of generics extend far beyond simple type safety. They enable code reuse across different data types, allowing you to write functions or classes that can handle a wide range of inputs without sacrificing clarity or performance. For instance, a generic sorting function can work with lists of integers, strings, or custom objects, as long as the necessary operations are defined. This reusability significantly reduces the amount of code you need to write and test. Additionally, generics improve type safety by catching errors at compile time rather than at runtime. This means that issues like adding an incorrect type to a list are detected before the code even runs, saving time during debugging. Furthermore, generics eliminate the need for explicit typecasting in most cases, which simplifies the code and reduces the risk of errors. They also support polymorphism by allowing you to define constraints that ensure the types used are compatible with the operations you perform. To define a generic class in Dart, you use angle brackets with a type parameter, such as T. For example, a box T class can hold a single value of any type. This flexibility is achieved by using the type parameter throughout the class's methods and properties. When writing methods that work with generic types, you can include the type parameter in the method signature. For instance, a method like tFindFirstList TList can return the first element of a list, regardless of the specific type it contains. Dart also allows you to add constraints to generic types using the extends keyword. For example, class box T extends num ensures that the type T must be a number, which restricts the possible values to integers, doubles, or other numeric types. Another important feature is type inference, which lets Dart automatically determine the type of a variable based on the context. For example, when you write var list equals 1, 2, 3, Dart infers the type as list int, eliminating the need to explicitly declare it. This reduces boilerplate code and makes the code more readable. Dart's type inference system is one of its most convenient features, as it automatically deduces the type of a variable based on the value it is assigned. For example, when you write var name equals Alice, Dart infers the type as string, and when you assign a list of numbers like var numbers equals 1, 2, 3, it infers the type as list int. This capability extends to more complex scenarios, such as when working with collections or function returns. Type inference not only saves time by reducing the need for explicit type declarations, but also makes the code cleaner and easier to understand. It works seamlessly with both primitive and custom types, allowing developers to focus on the logic of their code rather than the syntax of type declarations. By relying on type inference, you can write concise and expressive code that remains type-safe without the overhead of manual type annotations. Dart's advanced type inference goes beyond basic type detection, especially when working with null safety. Starting with Dart 2.12, non-nullable types are the default, which means that variables must have a value unless explicitly declared as nullable. For example, if a function returns a value, Dart infers its return type based on the logic inside the function. If the function calculates the sum of two numbers, the return type is inferred as int or double, depending on the inputs. However, when a variable might be null, you must explicitly declare it as nullable, such as string name equals null. This approach helps prevent null pointer exceptions by ensuring that null values are handled intentionally. In cases where type inference isn't sufficient, you can use the as keyword to perform explicit typecasting. For instance, if a variable's type is ambiguous, you can cast it to the desired type to resolve the ambiguity. This combination of inference and explicit control gives developers flexibility while maintaining safety. Generics are widely used in real-world applications to create versatile and reusable components. One of the most common use cases is building data structures like list, map, and set, which can hold elements of any type while ensuring type consistency. For example, a generic list T can store integers, strings, or custom objects, depending on how it is instantiated. Another key application is implementing generic functions for operations like sorting, filtering, or mapping. A a single generic function can process different data types without requiring separate implementations. This is particularly useful in APIs that need to handle dynamic data, such as a function that accepts a list of any type and returns a filtered version. Additionally, generics help maintain type consistency in complex object hierarchies, ensuring that operations on objects adhere to the expected types. By leveraging generics, developers can write code that is both flexible and safe, adapting to different scenarios without compromising on type integrity. To get the most out of generics in Dart, it's essential to follow best practices that prioritize clarity and safety. One of the most important guidelines is to prefer generics over using object or dynamic, as they provide stronger type safety and reduce the risk of runtime errors. While dynamic can be useful in certain cases, it sacrifices the benefits of compile time checks. Another best practice is to use type inference to simplify code where possible. For example, instead of writing list string names equals, you can use var names equals and let Dart infer the type. However, it's important not to overspecify types when the compiler can infer them automatically, as this can make the code more verbose. Finally, leverage type constraints to ensure that generic types meet specific requirements. For instance, if a class should only work with numeric types, you can use t extends num to enforce this restriction. By following these practices, you can write clean, efficient, and maintainable Dart code that is both robust and easy to understand. In conclusion, generics and type inference are fundamental concepts in Dart that empower developers to write safe, reusable, and maintainable code. Generics enable the creation of flexible data structures and functions that work with a wide range of types, while type inference simplifies the code by automatically determining types based on context. Together, these features reduce the likelihood of runtime errors and improve the overall quality of the code. By mastering generics, you can build abstractions that adapt to different scenarios without sacrificing type safety. Type inference further enhances productivity by minimizing boilerplate code and improving readability. As you continue to work with Dart, applying these concepts in real-world projects will deepen your understanding and help you write more efficient and reliable applications. Practice is key to mastering these tools, so don't hesitate to experiment different scenarios and explore their full potential. Mix-ins and abstract classes are advanced Dart features that allow developers to achieve code reuse and abstraction in more flexible ways than traditional inheritance. Mix-ins are particularly useful when you want to share functionality across multiple classes that may not have a common ancestor. They enable you to add methods and fields to a class without requiring a strict hierarchical relationship. On the other hand, abstract classes serve as blueprints for other classes, allowing you to define both abstract methods that must be implemented by subclasses and concrete methods that provide shared functionality. This dual approach helps in creating more structured and maintainable code bases by separating interface from implementation. Mix-ins are designed to be combined with other classes using the with keyword, which allows you to inject their methods and properties into a target class. Unlike regular classes, mix-ins cannot have constructors, which means they cannot be instantiated on their own. This restriction ensures that mix-ins are purely for code sharing and not for creating objects. They can include both concrete methods and abstract methods, which means they can provide some functionality while leaving other parts to be implemented by the class they are mixed into. This approach promotes composition over inheritance, making it easier to build modular and reusable code. By using mix-ins, developers can avoid the pitfalls of deep inheritance hierarchies and create more adaptable systems. Abstract classes are classes that cannot be instantiated directly, but they can serve as a foundation for other classes. They can contain abstract methods, which are methods without a body, and concrete methods, which have a complete implementation. This makes abstract classes ideal for defining a common interface that multiple subclasses must adhere to. Additionally, abstract classes can include constructors, fields, and static members, which allows them to carry state and behavior that can be shared across subclasses. This flexibility makes abstract classes a powerful tool for enforcing a contract between a base class and its subclasses, ensuring that certain behaviors are consistently implemented across different parts of the code base. When comparing mix-ins and abstract classes, it's important to understand their distinct purposes. Mix-ins are best suited for adding functionality to unrelated classes, allowing you to share code across across different parts of the system without forcing a hierarchical relationship. For example, a logging mix-in can be added to any class that needs to record events. Abstract classes, on the other hand, are used to define a common interface for related classes, such as different types of shapes in a geometry application. Another key difference is that mix-ins cannot have constructors, while abstract classes can. This means that abstract classes can initialize state when a subclass is created, whereas mix-ins rely on the target class to handle initialization. Choosing between the two depends on whether you need to share code across unrelated classes or define a shared structure for a family of related classes. To define a mix-in, you use the mix-in keyword followed by the name of the mix-in. For example, the logger mix-in includes a log method that prints a message. This method can then be used by any class that mixes in the logger. In the user service class, the with keyword is used to apply the logger mix-in, which adds the log method to the class. This allows the authenticate method to call log without needing to inherit from a superclass. The benefit of this approach is that it keeps the user service class focused on its primary responsibilities, while still gaining the ability to log messages. Mix-ins like logger are particularly useful for adding cross-cutting concerns, such as logging, caching, or validation to multiple classes without complicating their inheritance chain. An abstract class like shape defines a blueprint for its subclasses by declaring abstract methods that must be implemented. In this example, the area method is abstract, meaning that any class extending shape must provide its own implementation. The describe method, however, has a concrete implementation which provides a default behavior for all subclasses. This combination allows for both flexibility and consistency, as subclasses can choose to override the describe method if needed. The circle class extends shape, implementing the area method using the radius field. By defining the area method in the circle class, it ensures that the calculation is specific to a circle while still adhering to the shape interface. This structure makes it easier to manage different shapes in a system, as they all share the same base interface but can have unique implementations. When using mix-ins and abstract classes, it's important to follow best practices to maintain clarity and avoid unnecessary complexity. Mix-ins are most effective for adding orthogonal functionality, such as logging, caching or event handling, to classes that may not otherwise share a common ancestor. Abstract classes, on the other hand, are ideal for defining a common interface for a group of related classes, such as different types of data models or user interface components. It's advisable to avoid overusing mixins for complex hierarchies, as this can lead to confusion and maintenance challenges. Instead, combine mixins and abstract classes strategically to create a balance between code reuse and structural clarity. For instance, an abstract class might provide a base structure, while mixins add specific behaviors, resulting in a more modular and scalable design. In summary, mixins and abstract classes are essential tools in Dart for organizing and reusing code effectively. Mixins allow for composition-based code sharing, enabling developers to add functionality to multiple classes without relying on inheritance. Abstract classes provide a structured way to define interfaces and shared behavior, ensuring that subclasses adhere to a common contract. By understanding the strengths and limitations of each, developers can make informed decisions about when to use mixins or abstract classes. Whether building a simple application or a complex system, these features help in creating code that is modular, maintainable, and adaptable to changing requirements. Choosing the right approach depends on the specific needs of the project, but both mixins and abstract classes offer valuable ways to enhance code quality and reusability. Dart is a versatile language that extends beyond traditional front-end development to offer powerful capabilities for back-end development. It is designed to deliver high performance and scalability, making it an excellent choice for building robust server-side applications. One of its standout features is its support for asynchronous programming, which allows developers to handle I/O operations efficiently without blocking the main thread. This is particularly useful for managing multiple requests simultaneously, such as in APIs or real-time applications. Dart integrates seamlessly with popular frameworks like Aqueduct and Shelf, which provide tools to streamline the development of web services, APIs, and server-side logic. Whether you're building a simple API, a complex microservice, or a full-fledged server-side application, Dart offers the flexibility and tools needed to create scalable and maintainable solutions. A key strength of Dart for back-end development lies in its strong typing safety features. Strong typing ensures that variables and functions are explicitly defined, reducing runtime errors and improving code reliability. Null safety, a core feature introduced in recent Dart versions, helps prevent null reference exceptions by enforcing checks at compile time. This results in more robust and error-free code. Another significant advantage is the single code base approach, which allows developers to use the same language for both front-end and back-end development. This is possible because Dart can run on the Dart virtual machine for back-end tasks, while also being compiled to JavaScript for web applications. The rich ecosystem of packages available through pub/dev provides libraries for database interactions, HTTP requests, security protocols, and more, enabling developers to quickly implement complex functionality. Additionally, the Dart virtual machines just-in-time and ahead-of-time compilation capabilities ensure that applications run efficiently, offering both fast development cycles and optimized performance in production environments. When it comes to back-end development in Dart, several frameworks stand out. Aqueduct is a full-featured framework tailored for building REST-TFL APIs and web services. It includes built-in support for authentication, routing, and database interactions, making it ideal for creating scalable and secure backend systems. Shelf, on the other hand, is a lightweight middleware framework that provides flexibility for developers to construct custom HTTP servers. Its modular design allows for easy integration with other tools and libraries. Mojo is another framework designed for high-performance, real-time applications, leveraging Dart's asynchronous capabilities to handle WebSockets and other interactive features efficiently. Lastly, Dart Web is a term that highlights Dart's ability to bridge front-end and back-end development, enabling developers to use the same code base for both environments. This versatility makes Dart a unique choice for projects that require seamless integration between client and server components. Setting up a Dart backend project begins with installing the Dart SDK, which provides the necessary tools for development. Once installed, creating a project structure involves initializing a directory with a pubspec YAML file, which serves as the project's configuration and dependency manager. This file allows developers to specify packages like Aqueduct or HTTP, which are essential for building server-side logic. The next step is to create a main Dart file where the server's entry point is defined. This file typically includes a router configuration to map incoming requests to appropriate handlers. For example, defining routes for GET, POST, or other HTTP methods ensures that the server can respond to different types of client interactions. Finally, running the server can be done using commands like dart run or pub run, which execute the application and start the server, allowing developers to test their backend functionality locally. Developing REST-TFL APIs in Dart involves defining routes and handling requests using frameworks like Aqueduct or Shelf. Routes are typically configured using a router object, which maps specific endpoints to functions that process incoming requests. For instance, a GET request to a user's endpoint might retrieve a list of users, while a POST request to the same endpoint could create a new user. Implementing CRUD operations, create, read, update, delete requires defining methods for each HTTP verb, ensuring that the API can interact with data sources like databases. The request handling process often includes validating input data to ensure it meets expected formats, such as checking for required fields or data types. Structured responses, such as JSON objects, are then returned to the client, providing clear and consistent data exchange. By leveraging the asynchronous model of Dart, these operations can be performed efficiently, even under high loads. Integrating databases into a Dart backend project involves using packages like Postgres, MongoDart, or SQL Jockey, which provide drivers for connecting to various database systems. These packages allow developers to execute queries, manage connections, and interact with database records. For more complex applications, object relational mapping (ORM) tools can simplify database interactions by abstracting low-level SQL queries into higher-level operations. For example, an ORM might allow developers to create, read, update, or delete records using methods like save or find. Transactions and connection pooling are also critical for scalability, ensuring that multiple database operations can be executed reliably and efficiently. By leveraging Dart's asynchronous model, database interactions can be non-blocking, allowing the server to handle other requests while waiting for database responses. This approach optimizes performance and ensures that the application remains responsive even under heavy traffic. Security is a critical aspect of backend development, and Dart provides tools to implement robust security measures. Authentication mechanisms like JSON Web Tokens, JWT, or OAuth can be used to verify user identities and authorize access to API endpoints. Input validation and sanitization are essential to prevent attacks such as SQL injection or cross-site scripting, ensuring that user-provided data is safe to process. Using HTTPS for communication between clients and the server encrypts data in transit, protecting sensitive information from interception. Additionally, rate limiting and access control mechanisms can be implemented to prevent abuse of the API, such as limiting the number of requests a user can make within a specific time frame. These security practices help ensure that the backend remains secure, reliable, and compliant with modern standards. Optimizing the performance of a Dart backend involves leveraging its asynchronous model to handle I/O operations efficiently. By using async and await keywords, developers can write non-blocking code that allows the server to process multiple requests concurrently without waiting for each operation to complete. Caching strategies, such as using in-memory caches or external tools like Memcached, can reduce the load on the server by storing frequently accessed data. Optimizing database queries through indexing and batch processing ensures that data retrieval and manipulation are as efficient as possible. Monitoring and profiling the application with tools like Dart Dev Tools provides insights into performance bottlenecks, allowing developers to make data-driven improvements. These practices collectively ensure that the backend remains fast, scalable, and capable of handling high traffic demands. Dart's backend capabilities are well suited for a variety of real-world applications. For e-commerce platforms, Dart can power scalable APIs that handle product listings, user authentication, and transaction processing. Real-time chat applications can benefit from Dart's asynchronous model and WebSocket support, enabling instant message delivery and low-latency interactions. Microservices architectures can be built using Dart to create modular, independently deployable components that communicate over HTTP or other protocols. Integrating with third-party services such as payment gateways or analytics platforms is also straightforward thanks to Dart's rich ecosystem of HTTP and API libraries. These use cases demonstrate how Dart can be applied to solve complex problems across different industries, offering a reliable and efficient solution for modern software development. In conclusion, Dart provides a powerful and flexible environment for back-end development, combining speed, scalability, and ease of use. Frameworks like Aqueduct and Shelf simplify the creation of APIs and web services, while Dart's single codebase approach enables seamless integration with front-end development. Prioritizing security, performance, and scalability ensures that applications built with Dart are robust and ready for production. By exploring Dart's extensive ecosystem, developers can access a wide range of tools and libraries to build efficient, modern back-end solutions. Whether you're creating a simple API or a complex distributed system, Dart offers the capabilities needed to deliver high-quality, scalable applications. REST stands for Representational State Transfer and is a design approach for building networked applications. It relies on a stateless interaction between clients and servers, meaning each request contains all the information needed to process it. This makes systems more scalable and easier to manage. REST APIs use standard HTTP methods like GET, POST, PUT, and DELETE to perform actions on resources. For example, GET retrieves data, POST sends data, PUT updates it, and DELETE removes it. Data exchanged in REST APIs is commonly in JSON or XML format, with JSON being more prevalent due to its lightweight and easy-to-parse nature. Key principles of REST include a clear separation between client and server, a uniform interface for interactions, and the requirement that each request must contain all necessary information to be processed independently. Dart offers a powerful way to interact with REST APIs through the HTTP package, which simplifies making HTTP requests. This package provides methods such as GET, POST, PUT, and DELETE, allowing developers to easily send and receive data. For instance, the GET method fetches data from a specified URL, while POST sends data to a server. When building mobile applications with Dart, it is essential to grant internet permissions, especially for Android and iOS platforms. On Android, this involves adding a specific permission line in the Android manifest XML file. Dart also handles asynchronous operations efficiently using the async and await keywords, which make the code more readable and manageable by avoiding callback hell. This approach ensures that the application remains responsive even when waiting for network responses. To consume a REST API in Dart, you can start by fetching data from a public API, such as the one at JSON placeholder typicode com/posts. This example serves as a great way to practice and understand how APIs work. Once the data is retrieved, you need to parse the JSON response, which is where Dart's built-in Dart convert library comes into play. This library provides functions like JSON decode to convert JSON strings into Dart objects, making it easy to work with the data. However, it is crucial to handle errors that may occur during the process. For instance, network issues or invalid responses can cause exceptions, which can be caught using try-catch blocks. Here is an example of how to fetch and parse data. You use the HTTP GET method to send a request. Check the response status code, and then decode the body of the response into a Dart data structure. This process forms the foundation of working with APIs in Dart. Building a REST API with Dart can be accomplished using frameworks like Shelf or Aqueduct, which provide tools to create and manage web servers. These frameworks allow you to define routes and map them to specific functions that handle HTTP methods. For example, you can create a route that responds to a GET request by returning a simple message. The code snippet demonstrates how to set up a basic server with a route that returns "Hello, world" when accessed. Beyond the code, it is important to consider deployment options. Cloud services like Firebase or Oz offer scalable solutions for hosting your APIs, making them accessible to users worldwide. By leveraging these tools, developers can focus on building robust APIs without worrying about the underlying infrastructure. This combination of framework capabilities and cloud deployment options makes Dart a versatile choice for API development. When working with Dart and REST APIs, following best practices ensures reliability and maintainability. The HTTP package is a go-to choice for its simplicity and extensive community support, making it ideal for most projects. Implementing error handling is critical, as network requests can fail due to various reasons, such as connectivity issues or server errors. By using try-catch blocks, you can gracefully handle these failures and provide meaningful feedback to users. Security is another key aspect, especially when dealing with sensitive data. Techniques like API keys or OAuth can be used to authenticate users and protect your endpoints from unauthorized access. Structuring data with models helps in organizing and validating the information exchanged, reducing the risk of errors. Finally, testing your APIs with tools like Postman or Dart's test package ensures that they behave as expected under different scenarios, improving overall quality and user experience. REST APIs play a vital role in enabling communication between Dart applications and servers, allowing data to be exchanged seamlessly. The HTTP package in Dart simplifies this process, making it accessible even for developers new to API interactions. Building and consuming APIs requires a solid understanding of HTTP protocols, JSON data formats, and asynchronous programming concepts. These elements work together to create efficient and responsive applications. To truly master these skills, it is essential to practice with real-world examples, such as integrating APIs into mobile apps or building backend services. By applying theoretical knowledge to practical projects, developers can strengthen their ability to solve complex problems and create robust solutions that meet user needs. Dart security is essential for protecting applications from vulnerabilities and threats that could compromise user data and system integrity. When developing with Dart, it is crucial to focus on key areas such as data handling, authentication, input validation, and secure communication. These areas form the foundation of a robust security strategy. For instance, data handling involves ensuring that sensitive information is stored and transmitted safely. Authentication mechanisms verify user identities, while input validation prevents malicious data from exploiting system weaknesses. Secure communication ensures that data exchanged between the application and servers remains encrypted and tamper-proof. Proactive security measures are not optional. They are necessary to prevent breaches that could lead to data loss, financial harm, or reputational damage. By integrating security practices from the early stages of development, developers can build applications that users trust and that comply with modern security standards. Secure data handling in Dart requires careful attention to how sensitive information is stored and processed. Encryption is a critical tool for protecting data at rest and in transit. For example, using AES encryption for local storage or RSA for secure key exchange can prevent unauthorized access. Storing secrets such as API keys or passwords in plain text is a major risk. So developers should use libraries like Flutter Secure Storage, which provides encrypted storage for sensitive data. Additionally, user inputs must be sanitized to prevent injection attacks, such as SQL injection or cross-site scripting. This involves validating and filtering input data before processing it, ensuring that malicious code cannot exploit vulnerabilities in the application. By combining encryption, secure storage, and input validation, developers can significantly reduce the risk of data breaches and ensure that user information remains protected. Authentication and authorization are vital for controlling access to an application's resources and ensuring that only authorized users can perform specific actions. Implementing strong authentication methods such as OAuth or Firebase Auth allows users to verify their identities securely. These systems often use tokens to maintain sessions without storing sensitive credentials on the client side. Role-based access control, or RBAC, ensures that users have access only to the resources they need. For example, an admin user might have different permissions compared to a regular user. Managing tokens, such as JSON web tokens, requires careful handling. Tokens must be signed with strong algorithms, have expiration times, and be stored securely to prevent interception or reuse. By combining robust authentication mechanisms with strict authorization policies, developers can create applications that are both secure and scalable. Input validation is a fundamental practice in Dart development to prevent malicious data from causing harm. Every input, whether from a form, API request, or user interaction, must be validated to ensure it meets expected criteria. For example, using Dart's regexp class, developers can define patterns to check if input matches a specific format, such as an email address or phone number. However, relying solely on client-side validation is insufficient, as attackers can bypass it. Server-side validation is essential to enforce rules consistently. Imagine a scenario where a user submits a form with malicious code without proper validation. This code could execute in the application or database. By implementing validation at both ends, developers can mitigate risks such as SQL injection or cross-site scripting. This dual-layer approach ensures that only safe, well-formed data is processed, enhancing the application's security. Secure communication in Dart applications is critical for protecting data as it travels between the client and server. Enforcing HTTPS for all network requests ensures that data is encrypted using SSL/TLS protocols, making it difficult for attackers to intercept or alter. The HTTP package in Dart supports secure communication by default, but developers must verify that SSL/TLS configurations are correctly implemented. Hard-coding API keys or other sensitive information in client code is a common mistake that can lead to exposure. Instead, developers should use environment variables or secure storage solutions to manage these secrets. Additionally, APIs should be designed with security in mind, such as by limiting request rates, validating endpoints, and using secure authentication methods. By prioritizing secure communication, developers can protect user data and maintain compliance with industry standards. Effective error handling and logging in Dart applications require a balance between providing useful information to developers and avoiding the exposure of sensitive details. Error messages should be generic enough to prevent attackers from gaining insights into the application's internal workings. For example, instead of revealing database structure or file paths, errors should indicate general issues like invalid request or server error. Logging errors securely involves using tools like the logging package, which allows filtering and storing logs in a controlled manner. Developers should implement try-catch blocks to handle exceptions gracefully, ensuring that the application does not crash unexpectedly. By logging errors without exposing sensitive data, developers can diagnose issues while maintaining the application's security posture. The secure use of third-party libraries in Dart requires vigilance to avoid introducing vulnerabilities into the application. Developers should regularly update dependencies using tools like Dart Pub, outdated to ensure they are using the latest versions with security patches. Auditing libraries for vulnerabilities can be done with static analysis tools such as Dart Analyze, which checks for potential issues in the code base. Additionally, developers must be cautious about using untrusted packages, especially those with excessive permissions or unclear licensing. For example, a package that requests unnecessary access to the device's camera or location might pose a risk. By maintaining a clean and well-audited dependency list, developers can reduce the attack surface of their applications and stay ahead of emerging threats. Secure storage practices in Dart applications are essential for protecting sensitive data such as user credentials, tokens, and personal information. Using Flutter Secure Storage is recommended for storing such data, as it provides encrypted storage that is accessible only to the application. For local storage, developers can use the encrypt package to implement additional layers of encryption, ensuring that even if data is accessed, it remains unreadable. Avoiding the use of shared preferences or local files for storing credentials is crucial, as these methods are vulnerable to attacks if not properly secured. For example, storing a password in a shared preference file could allow an attacker to retrieve it if the device is compromised. By adopting secure storage strategies, developers can minimize the risk of data exposure and protect user privacy. Code security practices in Dart development involve a combination of proactive measures and continuous monitoring. Conducting regular code reviews helps identify potential security flaws that may have been overlooked during development. Static analysis tools like Dart Analyze can detect issues such as insecure code patterns, unused variables, or potential vulnerabilities. Hard-coded secrets, such as API keys or passwords, should be avoided entirely, as they can be easily extracted from the source code. Instead, developers should use environment variables or secure storage solutions. By integrating security into the development workflow, teams can ensure that their code remains resilient against attacks and adheres to best practices. In conclusion, Dart security is an ongoing process that requires attention to detail, adherence to best practices, and a commitment to continuous improvement. Developers must prioritize data protection by implementing encryption, secure storage, and input validation. Ensuring secure communication through HTTPS and proper token management is equally important. Staying updated with the Dart ecosystems security updates and community guidelines helps developers address emerging threats proactively. By fostering a culture of security awareness and integrating these practices into every stage of development, teams can build applications that are not only functional, but also resilient against evolving security challenges. Performance optimization is a critical aspect of building efficient and user-friendly Dart applications. When applications run smoothly, users are more likely to engage with them, which directly impacts the success of any project. However, even the most well-designed apps can suffer from performance issues if not carefully managed. Common performance bottlenecks include memory leaks, which occur when objects are not properly released from memory, leading to increased memory usage over time. Inefficient algorithms can cause delays in processing, especially with large datasets, while excessive UI re-renders can make the app feel sluggish. The primary goals of performance optimization are to improve responsiveness by reducing delays, minimize resource usage such as CPU and memory, and ultimately create a seamless and enjoyable user experience. By addressing these areas, developers can ensure their apps remain fast, reliable, and scalable. Dart provides powerful tools for profiling and analyzing application performance. Dart Dev Tools is an essential platform that allows developers to monitor real-time metrics such as CPU usage, memory allocation, and frame rates. These metrics help identify where the app may be consuming excessive resources or experiencing delays. For example, high CPU usage might indicate a computationally heavy task, while frequent memory allocations could point to unnecessary object creation. The observatory tool complements this by offering deeper insights into the Dart VM, enabling debugging and optimization of specific code sections. By leveraging these tools, developers can pinpoint performance issues, test fixes, and ensure their apps run efficiently across different devices. Effective memory management is crucial for maintaining optimal performance in Dart applications. One key strategy is to avoid creating unnecessary objects, as each object consumes memory and can contribute to garbage collection overhead. Instead, developers should reuse objects where possible, especially in loops or frequently called functions. Using final variables and const keywords for immutable data helps prevent unintended modifications and reduces memory allocation. For instance, declaring a widget as const ensures it is created once and reused, which improves rendering efficiency. Additionally, the Dart Dev Tools Memory Profiler provides detailed insights into memory usage, allowing developers to track allocations, identify memory leaks, and optimize their code for better performance. Asynchronous programming is a cornerstone of building responsive Dart applications. Using async and await allows developers to perform non-blocking operations, such as network requests or file I/O, without freezing the UI. This ensures the main thread remains free to handle user interactions. However, long-running synchronous tasks on the main thread can cause jank and unresponsiveness, so it is essential to offload such work to background threads. For CPU-intensive tasks, isolates provide a way to run code in separate threads, preventing the main thread from becoming overwhelmed. By mastering async programming and isolates, developers can create applications that remain smooth and efficient even under heavy workloads. Optimizing the structure of Dart code can significantly improve performance, especially in frameworks like Flutter. Minimizing nested widgets reduces the complexity of the widget tree, which in turn speeds up rendering. For example, excessive nesting can lead to unnecessary rebuilds and increased memory usage. Stream and future optimization techniques, such as using where or map to filter or transform data, help avoid redundant computations. Additionally, caching and memoization can prevent repeated calculations by storing results for later use. These practices not only enhance performance, but also make the code base more maintainable and scalable. Reducing UI overhead is essential for creating fast and efficient user interfaces. Utilizing const constructors for immutable widgets ensures they are created once and reused, which improves rendering performance. Optimizing build methods involves avoiding unnecessary rebuilds by using keys, state management strategies, or leveraging the Flutter performance overlay to visualize frame rates and identify bottlenecks. For instance, the overlay can highlight areas where the app is dropping frames, guiding developers to focus their optimization efforts. By combining these techniques, developers can create UIs that are both visually appealing and performant. Avoiding common pitfalls is vital for maintaining optimal performance in Dart applications. Overusing set state in Flutter can trigger unnecessary rebuilds, leading to sluggish UI updates. To mitigate this, developers should use state management solutions like Provider or Riverpod to control when and how the UI updates. Large lists without pagination or lazy loading can cause memory issues and slow rendering. So implementing techniques like scrolling or virtualization is crucial. Additionally, poorly optimized image loading can result in high memory usage and slow load times. Using image caching strategies, such as the Flutter Cache Manager package, ensures images are loaded efficiently and reused when possible. In summary, performance optimization in Dart involves a combination of profiling, memory management, and asynchronous best practices. Regular performance testing and code reviews help catch issues early, ensuring the app remains efficient as it evolves. For advanced optimization, developers can explore Dart VM tuning, such as adjusting garbage collection settings, or implement custom memory management techniques for specific use cases. By staying proactive and continuously refining their code, developers can create applications that deliver exceptional performance and user satisfaction. Welcome to this session on advanced Dart patterns and practices. Today, we will explore techniques that elevate your Dart code to new levels of quality, scalability, and maintainability. We will dive into design patterns, best practices, and how to apply them in real-world scenarios. Whether you are building small apps or large-scale systems, these concepts will help you write cleaner, more efficient, and more robust code. Let's begin by understanding the importance of these practices in modern Dart development. The singleton pattern is a powerful tool in Dart for ensuring a single instance of a class throughout your app's lifecycle. This is particularly useful for managing shared resources like configuration settings or database connections. To implement a singleton, you use a private constructor to prevent direct instantiation and a static variable to hold the single instance. For example, the app settings class in the code snippet demonstrates this by creating a static final instance of the class. This approach guarantees that all parts of your app access the same instance, promoting consistency and reducing overhead. However, be cautious with overusing singletons, as they can introduce tight coupling and make testing more challenging. When it comes to object creation, the factory and builder patterns offer distinct advantages. The factory pattern centralizes the logic for creating objects, which simplifies complex instantiation processes. For instance, a factory method in the user class can handle different input formats, such as parsing JSON data. On the other hand, the builder pattern is ideal for constructing complex objects step by step. Imagine creating a user profile with multiple optional fields. Using a builder allows you to set properties incrementally, improving readability and flexibility. Both patterns help decouple your code from specific implementation details, making it easier to maintain and extend. Null safety is a cornerstone of modern Dart development, and mastering its best practices can prevent a wide range of runtime errors. By leveraging non-nullable types, you ensure that variables are always initialized, reducing the risk of null references. Use the required keyword for parameters that must be provided and employ null-aware operators like and to handle optional values gracefully. Late variables should be used sparingly, as they require explicit initialization. For example, a late final variable might be appropriate for a value that is initialized after the object is created, but before it is used. Prioritizing null safety makes your code more predictable and easier to debug. Asynchronous programming is essential for building responsive and efficient Dart applications. The future and stream classes enable non-blocking operations, allowing your app to remain fluid during tasks like network requests or file I/O using async await syntax makes asynchronous code more readable and manageable, as it avoids the complexity of nested callbacks. For example, the fetch data function in the code snippet demonstrates how to use async await to retrieve data without freezing the UI. By structuring your code with futures and streams, you can handle complex workflows and user interactions more effectively. Organizing your code effectively is key to maintaining large projects. Modularizing your code into packages, services, and models helps separate concerns and improves reusability. The part and library directives allow you to split code into multiple files, making it easier to navigate and manage. For instance, a library might group related functions, while part files break down a large class into smaller, focused components. Additionally, adopting the MVVM architecture ensures a clear separation between the user interface, business logic, and data models. This structure not only enhances maintainability, but also simplifies testing and collaboration among team members. Advanced type safety techniques in Dart go beyond basic types, enabling more flexible and reusable code. Generics allow you to create classes and methods that work with any type, reducing code duplication. For example, a generic network response class can handle different data types returned from an API. Typedefs provide aliases for complex function types, making your code more expressive. Extensions, on the other hand, let you add new methods to existing types without modifying their source code. These features collectively enhance type safety, improve code clarity, and empower you to write more robust and scalable applications. To recap, mastering advanced Dart patterns and practices is crucial for solving complex problems and building high-quality applications. Prioritize null safety to prevent runtime errors. Design asynchronous code with futures and streams, and adopt clean architecture to ensure scalability. By applying these best practices, you can create Dart applications that are not only functional, but also maintainable and adaptable to future changes. Remember, the goal is to write code that is easy to understand, test, and extend principles that will serve you well in any project. Thank you for your attention, and I hope you leave with actionable insights to enhance your Dart development skills. Full-stack development in the context of Dart refers to the ability to build both the client-side and server-side components of an application using the Dart programming language. Dart is uniquely positioned as a versatile language that powers Flutter for front-end development, allowing you to create responsive user interfaces for mobile, web, and desktop platforms. On the back end, Dart can be used with frameworks like Aqueduct or Shelf to build scalable server-side applications. Throughout this session, we will explore how to combine these capabilities to build a complete application, from the user interface down to the server and database. By the end, you will have a clear understanding of how Dart can streamline the entire development lifecycle. When it comes to front-end development with Flutter, the framework enables you to create cross-platform applications with a single code base. This means you can build apps for mobile devices, web browsers, and desktop environments using the same Dart code. Key components of Flutter development include widgets, which are the fundamental building blocks of the UI. These widgets can be combined to create create complex layouts and interactive elements. State management is another critical aspect, and we will discuss tools like Provider and Riverpod to efficiently manage the app state. Navigation is also essential, and we will cover how to transition between screens and pass data between them. Additionally, integrating APIs allows your app to fetch dynamic data from external sources, making your application more interactive and functional. For backend development with Dart, we have several frameworks to choose from, including Aqueduct, Shelf, and Firebase. Each of these tools offers different levels of flexibility and features. Aqueduct is a robust framework for building REST-TFL APIs, while Shelf provides a lightweight approach for creating server-side logic. Firebase, on the other hand, offers a managed backend solution with real-time database capabilities. When designing APIs, we will focus on REST-TFL principles, ensuring that endpoints are well structured and follow standard HTTP methods. Server-side logic will involve implementing business rules, such as data validation and authentication, to ensure the application functions securely and efficiently. This section will also cover how to handle user authentication and manage data flow between the front end and back end. Database integration is a crucial step in building full-stack applications. Dart supports various database systems, including relational databases like PostgreSQL and NoSQL databases like MongoDB. To interact with these databases, we will use Dart packages such as Postgres for PostgreSQL and MongoDart for MongoDB. These packages provide methods to perform CRUD operations, query data, and manage database connections. Security is a top priority, so we will discuss best practices for storing and retrieving data securely, such as encrypting sensitive information and implementing proper access control. By the end of this section, you will understand how to connect your Dart backend to a database and ensure data integrity and protection. Establishing communication between the front end and back end is essential for any application that requires dynamic data exchange. In Dart, we can use the HTTP package or the more feature-rich DO package to make API calls from the front end to the back end. These packages allow you to send HTTP requests, handle responses, and manage errors effectively. Authentication is another critical aspect, and we will explore methods like JWT JSON Web Token to secure API endpoints. Data serialization, such as converting data to and from JSON format, will also be covered, ensuring that data is correctly formatted for transmission. By mastering these techniques, you will be able to build applications that seamlessly interact with backend services. Real-time features can enhance user experience by allowing instant updates and interactions. In Dart, we can implement real-time functionality using WebSockets or Firebase's real-time database. WebSockets enable bidirectional communication between the front end and back end, making them ideal for applications like chat systems or live notifications. The WebSocketChannel package simplifies the process of establishing and managing WebSocket connections. We will demonstrate how to use these tools to create a chat application that updates in real time. This section will also highlight the advantages of real-time features and provide practical examples to illustrate their implementation. Testing and debugging are vital to ensuring the reliability and quality of your Dart applications. We will discuss writing unit tests for backend logic and widget tests for Flutter UI components. Tools like Test and FlutterTest will be used to automate testing, while Makito will help simulate dependencies for more controlled testing scenarios. Debugging can be done using Dart Dev Tools for performance analysis and Flutter Inspector for examining the UI hierarchy. By incorporating testing into your workflow, you can identify and fix issues early, leading to more robust applications. This section will provide hands-on examples of how to test and debug both front-end and back-end code effectively. Deployment strategies ensure that your application reaches users efficiently. For the front end, we will cover how to publish a Flutter app to app stores like Google Play and the Apple App Store, as well as deploy web applications to platforms like Firebase Hosting or Netlify. On the back end, we will explore cloud services such as Google Cloud, AWS, or Versal for hosting server-side code, configuring CI/CD pipelines with tools like GitHub Actions or GitLab CI will automate the deployment process, making releases faster and more reliable. This section will guide you through the steps of preparing your application for production and ensuring it is scalable and maintainable. Adhering to best practices is essential for creating maintainable and scalable Dart applications. We will discuss clean architecture patterns like MVC Model View Controller and below-C Business Logic Component to organize code effectively. Security is a priority, so we will cover implementing authentication mechanisms such as OAuth and JWT to protect your APIs, performance optimization techniques, including efficient state management and minimizing resource usage, will also be addressed. By following these best practices, you can build applications that are not only functional, but also easy to maintain and extend over time. In conclusion, this session has covered the entire process of building a full-stack Dart application, from front-end development with Flutter to back-end logic, database integration, and deployment. Dart's ecosystem offers a unified approach to development, allowing you to use the same language across all layers of your application. By practicing with sample projects and real-world scenarios, you can deepen your understanding and apply these concepts effectively. As you continue your journey with Dart, remember that consistent practice and exploration of its tools will help you become a proficient full-stack developer. And just like that, our dreamy coding adventure has come to an end. I hope the gentle ebb and flow of the tutorial, combined with the tranquil melodies, have left you feeling both informed and at ease. Whether you managed to catch every line of code or drifted off into a peaceful slumber, remember that the world of Dart will always be here waiting for you. Keep your code clean, your mind open, and your spirit relaxed. Don't forget to subscribe to Code Snooze so you never miss out on another soothing coding journey. Hit that like button if this video brought you a moment of calm and learning, and share it with fellow coders or anyone in need of a serene study session. Thank you for joining me in this cozy corner of the internet. Until next time, may your code run smoothly and your dreams be filled with brilliant algorithms. Sweet dreams, sleepy coders.